There's a hum in the room right now, not the galaxy, just whatever machine in your house is doing its quiet overnight work. The refrigerator maybe, or the ventilation in the walls pushing air through passages you never think about. It's the kind of sound you only notice when everything else goes still. And noticing it doesn't mean anything, it's just there, a texture in the silence. That's where this starts. Not with space, not yet. With the feeling of a room having edges and your body knowing where they are without looking. You've had this feeling before, standing at the edge of something, a building's rooftop, a field that ends at a tree line, a conversation that's approaching its natural end and sensing the boundary before you reach it. Something in the body reads it. A shift in air pressure maybe, a change in sound, some quiet signal that you are near the limit of a defined space. The Milky Way doesn't give you that signal. And this is the thing worth sitting with tonight. The galaxy has a boundary of some kind. That's not in question. Matter thins as you move outward from the core. The disk of stars, the flat spiral structure we live inside, has a rough shape, a rough edge. Astronomers talk about it in terms of where the density drops below a certain threshold, where the stellar population becomes sparse enough that galaxy stops being a useful word for what surrounds you. It's somewhere around 50,000 light years from the center, give or take quite a lot actually. The number shifts depending on what you're measuring. Stars, gas, dark matter. Each one draws a different boundary in a different place. So there isn't one edge, there are several, overlapping depending on what you ask. That's already a strange thing to sit with, that a boundary can be multiple, simultaneous, none of them quite authoritative. Here's what I keep coming back to. The edges we trust most are the ones we can feel. A table's edge, you know exactly where it is. The end of a mattress, the point where pavement becomes grass. These are edges that exist because material stops and something else begins. There's a moment of transition, and it's sharp enough that your body registers it. Galactic edges aren't like that. They're more like, and I'm going to try to find the right word here, because gradient is technically correct but somehow too tidy. They're more like the edge of a conversation when no one has quite said goodbye. You're still in it. And then at some point, without a clear moment of ending, you aren't. You were at the boundary the whole time and you didn't feel it pass. The sun sits roughly 26,000 light years from the galactic center. Not at the edge, not near the core, in the disk, in the middle latitudes of the galaxy's thin disk structure, orbiting at a speed of about 220 kilometers per second. This is a number, 220 kilometers per second, that I find genuinely hard to hold in the mind. Not because it's large, but because it's invisible. You don't feel it. The chair you're in doesn't vibrate with it. There's no wind, no sensation of motion, nothing pressing you backward into your seat. All of that speed and the body reports nothing. This is one of the stranger facts about existing in a galaxy. The motion is total and the sensation is zero. When you look up at the night sky, if you've been somewhere dark enough to really look, somewhere without light pollution bleeding into the horizon, somewhere the Milky Way shows itself as an actual smear of light rather than a rumour, you are looking across the disk. The dense band of stars above you is the galaxy seen from inside, looking roughly toward the plane of the structure you're part of. You're not above it, not below it. You're inside the plane, looking along it. This means something subtle. It means there is no vantage point from which any of us has ever seen the full shape of the thing we live inside. Every photograph you've seen of the Milky Way, the sweeping spirals, the glowing core, the arms reaching outward, is a composite, a reconstruction, a combination of infrared maps and radio telescope data, and a lot of very careful inference. We've never actually seen it from outside. We're working from descriptions assembled inside the room, which brings you back to the edge. If you can't see the shape of the structure from outside, can you meaningfully approach its boundary? What would approaching the edge even feel like if the edge isn't a surface, isn't a wall, isn't a transition sharp enough for instruments to agree on? You'd be moving through progressively thinner distributions of stars, fewer neighbours, longer gaps between gravitational influences. The background radiation of the galaxy's collective mass would quiet slightly, not vanish, and at some point, no particular point, the word inside would stop applying with the same confidence. That's not a dramatic edge, it's an administrative one almost, a category boundary rather than a physical one. I'm not sure that makes it less real. Or, no, wait, that's not quite right. Let me think about this differently. A fog has an edge, not a sharp one, but you can still say there is a place where the fog is and a place where it isn't, even if the transition between them is long and gradual and you were already wet before you realized you'd entered it. The edge existed even if you couldn't feel the moment of crossing. Galaxies might be like that, an edge that you could only identify in retrospect, looking back at where the density of stars used to be, realizing that somewhere behind you the word inside stopped describing your position. You could spend a long time moving towards that edge, a very long time. At any speed human technology can currently produce, the time required to reach even the outskirts of the Milky Way would exceed any frame of reference you could meaningfully hold. Voyager 1, the farthest object humanity has ever launched, is, as of now, roughly 23 billion kilometers from the Sun. This sounds enormous. It is enormous, and it represents less than 1% of a single light year. The disk of the Milky Way is roughly 100,000 light years across. At Voyager's speed, roughly 17 kilometers per second, which is not slow, it would take about 37,000 years to travel 1 light year. The galaxy's radius is approximately 50,000 light years. The math is not encouraging, but I want to stay with something else, not the impossibility of the distance because that becomes numbing quickly, more the feeling of an edge that you move toward and that keeps receding. Not because someone is pulling it back, but because the nature of the edge is exactly this. It doesn't snap into focus as you approach. It diffuses, it thins, it becomes a region rather than a line, and then a tendency rather than a region, and then a kind of statistical quiet where things used to be. There's a specific quality to that experience, if you could have it. An edge you couldn't feel approaching, a boundary you could only identify after it had passed. Not a wall, not a threshold, something more like the end of a thought when you're falling asleep. You can't find the last moment you were still awake, but at some point you clearly weren't anymore. Outside, not far just through the glass, the night is doing its ordinary work. Stars are visible or they aren't, depending on cloud cover. The galaxy is up there regardless. Its core is somewhere below your horizon right now, or above it, spinning at its slow, vast pace. The 400 billion or so stars in this structure are each doing their own complicated thing. Most of them are smaller and cooler than the Sun. Many of them are very old. A few of them have planets. None of this is pressing on you. None of this asks anything of you tonight. The edge you keep approaching, of sleep, of the day, of this thought, is probably closer than the galaxy's boundary. And unlike the galactic outskirts, this edge will arrive. You'll find it, or it will find you. The galaxy's edge will just keep being what it is, approximate, distributed, dependent on what you're measuring, and located somewhere that's both real and slightly impossible to point to. Not hiding, not moving, just not a line, which is, when you stay with it, a quieter kind of boundary than the ones you usually trust. There's more to the story of this place we're in. This 100,000 light-year structure will never leave from any vantage that matters. The force that keeps us here isn't just distance. It's something built into the geometry of the whole, a pull that exists not because anything is pulling exactly, but because of what mass does to the space around it, and what space then does to everything moving through it. That's the next thing. That's what's waiting. Somewhere in the dark past this thought. Pick up a stone. Not a remarkable one. Something ordinary, roadside, the kind of rock that's been rained on so many times it's forgotten what it looked like when it was broken off from something larger. Hold it in your palm, feel the weight of it pressing down. Not much weight. A few grams, maybe. The kind of weight you stop noticing after a few seconds because the hand adjusts, the muscles compensate, and the pressure becomes just another piece of background sensation that the body quietly absorbs. That downward pull, that stubborn, unremarkable drag, is gravity, not a metaphor for it, not a simplified version of it. That specific, dull, familiar pressure is the same force that holds the Milky Way together, the same mechanism, the same physics, scaled up by a factor so large the comparison becomes almost meaningless, but still the same. There's something worth sitting with in that. Gravity isn't generated by a source the way heat radiates from a fire, where you can point at the thing producing it and feel the output diminishing as you back away. It's more structural than that. Mass curves the geometry of the space around it, not curves as a loose metaphor, but as a literal, measurable distortion of space-time, confirmed to extraordinary precision by observations ranging from GPS satellite corrections to the direct detection of gravitational waves, and other objects moving through that curved geometry follow paths that bend toward the mass responsible. They're not being pulled in the way a rope pulls. They're moving in straight lines through a space that has been shaped into curves. The stone in your hand falls not because the earth is reaching up and grabbing it, but because the geometry of space in your immediate vicinity tilts very steeply toward the planet's center, and an object released into that geometry has nowhere else to go. Now remove the stone, remove the hand, remove the room. What remains is the principle. The Milky Way has a mass, a total mass, somewhere in the range of 1 to 2 trillion times the mass of the Sun. That number varies depending on how far out you measure, how much dark matter you attribute to the structure, which models you trust. But the rough shape of the number is that 1 trillion solar masses, give or take, arranged across a disk roughly 100,000 light-years wide, with a dense central bulge and a spherical halo of material, and much of it invisible, extending well beyond the visible disk. All of that mass is curving space-time constantly, in every direction outward from every particle of it. The curvature from a single star is negligible at galactic distances, but 1 trillion stars, plus the gas, the dust, the dark matter, threading through everything, produce a cumulative gravitational geometry so deep and so wide that objects orbiting at the galaxy's outskirts are still, after billions of years, tracing closed paths, still bound, still falling through the curved space the galaxy's collective mass has produced around itself. This is what gravity remembers, not events, not history in any narrative sense. But mass, the existence of mass, persists in space-time as geometry, and that geometry accumulates. The Sun's gravity reflects the process that formed it, the slow gravitational collapse of a gas cloud roughly 4.6 billion years ago. The galaxy's gravitational field reflects something older than that, the long process of hierarchical assembly, by which small overdensities in the early universe drew matter together, merged, grew, attracted more matter, grew further, until structures of galactic scale had assembled themselves over hundreds of millions of years from nearly smooth initial conditions. What you're held by right now is the product of all of that accumulation, the gravitational signature of a process that began when the universe was a fraction of its current age. There's something about dark matter that keeps snagging attention here, and it's worth pausing on it because it isn't peripheral to this story, it's close to the center of it. The visible matter in the Milky Way, the stars, the gas clouds, the dust, would not, on its own, produce enough gravitational force to explain how the galaxy behaves. Stars in the outer disk orbit faster than they should, if the only mass present were the mass we can see. This discrepancy was noticed seriously in the 1970s. Vera Rubin and Kent Ford measuring the rotation curves of galaxies, finding the flatness that visible matter alone could not account for. And it has never been resolved by finding a conventional explanation. The best supported interpretation remains that galaxies are embedded in vast halos of matter that interacts gravitationally but not electromagnetically. It doesn't emit light, it doesn't absorb light, it doesn't interact with the photons by which we see anything at all. It is, in the most literal sense, invisible. And it outweighs the visible matter in the Milky Way by a factor of roughly 5-1. 5-1, which means that the gravitational hold you're inside right now, the curvature of space-time that keeps the solar system orbiting the galactic center, that keeps the galactic disk from flying apart, that keeps you, in some deep structural sense, inside this galaxy rather than drifting freely through intergalactic space, is mostly produced by something that has never been directly detected, never been seen, known only through its effect on the motion of things we can see. This is where I find myself pausing, not in a troubled way, more in the way you pause when a fact takes a moment to fully settle. You're gravitationally held by matter that cannot be observed through any electromagnetic means currently available to human science. The force shaping your cosmic situation is, in its majority contribution, produced by stuff whose fundamental nature remains genuinely unknown. That isn't dramatized, it's just true. The halo of dark matter surrounding the Milky Way extends well beyond the visible disk. Estimates vary, but the dark matter halo likely stretches outward for several 100,000 light-years in all directions, far beyond the stellar population, far beyond the gas clouds, far beyond anything you'd see in an optical image of the galaxy. It is a vast, roughly spherical structure surrounding the disk we inhabit, and its gravitational influence is what stabilizes the rotation of the outer galaxy and keeps the whole structure coherent across cosmic time. You're not just inside the Milky Way's disk, you are deep inside its gravitational halo. The two things are not the same, and the halo is the larger of them, and you would have to travel through a significant fraction of it before you'd be far enough from the galaxy's total mass to consider yourself free of it in any physically meaningful sense. Gravity falls off with distance. This is familiar, the inverse square law, the way a light source dims as you move away from it following the same mathematical rule. Double the distance and the gravitational force drops to 1/4 of its previous value. The force thins as you recede, but thins is not the same as disappears. At the distance of the Andromeda galaxy, roughly 2.5 million light-years, the Milky Way still exerts a gravitational influence, not dominant, not the primary force shaping Andromeda's trajectory, but present, measurable in principle, woven into the overall gravitational accounting of the local group, the loose collection of galaxies of which the Milky Way and Andromeda are the two largest members. Gravity has extraordinary range. It falls off, yes, but it never reaches zero. Every mass in the universe exerts a gravitational influence on every other mass, however small, however attenuated by distance. The Milky Way is pulling on objects billions of light-years away with a force so small it's essentially nothing. But Essentially nothing is not the same as nothing. The stone again, back in your hand if you want it. The weight of it is the Earth's gravity at the surface, about 9.8 meters per second squared of acceleration, which is the product of Earth's mass and your distance from its center, according to the same equation that governs the solar system's orbit around the galactic core. The numbers differ enormously. The mass differs enormously. The distances differ enormously. But the form of the relationship is identical. This is one of those facts that sounds like a pleasantry. The same force that holds galaxies also holds stones, but is worth taking more literally than that. Gravity isn't a family of related phenomena operating by different rules at different scales. It's one thing, a single geometric principle with a single mathematical description, operating unchanged from the scale of falling fruit to the scale of galaxy clusters. The stone knows this, in whatever sense a stone can know anything. It falls the way it falls because space-time curves the way it curves, and space-time curves the way it curves because mass exists the way it exists. There's a word that keeps coming up in discussions of gravity, and it's felt. We feel gravity. We don't feel electromagnetism in the same direct bodily way. We experience its consequences through sight, through the solidity of objects, through warmth. But the force itself isn't registered as a pull or a pressure by anything in the human body in the way that gravity is. Gravity is the one fundamental force with an immediate, continuous somatic presence. You are feeling it right now, in the weight of your body against whatever is supporting it, in the slight pressure of your head resting, or your hands resting, or your eyelids. Even your eyelids have weight, a fact that becomes noticeable in the particular heaviness that comes with real tiredness, the gravitational surrender of eyes that stop wanting to stay open. The galaxy's gravity is in there too, technically, impossibly small at human scales, immeasurable against the Earth's surface gravity, but present, folded into the total gravitational accounting of the mass surrounding you, the cumulative curve of space-time that every massive body in the universe has contributed to in some infinitesimal way. What gravity remembers then is this: it accumulates without forgetting. Every mass that has ever been assembled, every star that formed from a collapsing gas cloud, every merger of smaller galaxies into larger ones, every patient coalescence of dark matter into the halos surrounding structures like ours. All of that assembly persists as gravitational geometry. It doesn't fade the way heat fades. It doesn't dissipate the way sound dissipates. It just continues, shaping the paths of everything moving through the space it has curved. The Milky Way has been building its gravitational memory for roughly 13 billion years. What you are held by tonight is the product of that entire duration, not a static thing, not finished. The galaxy is still accreting material, still slowly pulling in smaller satellite structures, still deepening the gravitational well at its center. The memory is still being written, and somewhere in all of that, in the trillion solar masses, in the dark matter halo, in the slow orbital mechanics of 400 billion stars, is the Sun, and around the Sun, at a distance of about 150 million kilometers, is this planet. And on the surface of this planet, under whatever darkness is outside your window, is the body you're in, held. Not in a way that asks anything of you, not in a way that announces itself, except in the ordinary weight of things. There's a thought that follows from all this, about what it would actually take to leave, about the velocity required and where that number comes from and what it quietly reveals about the nature of the hold. That thought is close. There's a number, not a complicated one, not buried in tensor equations or requiring a specialist to locate. It's a clean number, derivable from two pieces of information: the mass of the thing you're trying to leave and your distance from its center. Feed those in, and what comes out is a speed, a specific speed, below which you cannot escape and above which you can. That's it. That's the whole mechanism. And yet, the escape velocity from Earth's surface is approximately 11.2 kilometers per second, 40,000 kilometers per hour roughly. Fast enough that a projectile launched straight up at that speed, ignoring air resistance, ignoring everything, would never fall back. Not because it outran gravity. Gravity would still be acting on it, still decelerating it the whole time, but it would be decelerating into an asymptote rather than a turnaround. The speed would bleed off and approach zero, but approach zero at the same rate that the gravitational force was also approaching zero. The two things thinning together, neither one winning. The projectile coasting forever through increasingly empty space, technically still slowing, technically never fully stopped. That's what escape means, physically. Not breaking free, asymptotically outrunning the deceleration. From the solar system's position within the Milky Way, 26,000 light-years from the center, embedded in the disk, inside the dark matter halo, the escape velocity is somewhere around 550 kilometers per second. Some estimates put it closer to 500. Others push it towards 600, depending on assumptions about the dark matter distribution and the total mass of the halo extending beyond the visible galaxy. Call it 550. The uncertainty in the number doesn't change its character. 550 kilometers per second. To leave. Voyager 1, the fastest continuously traveling object humanity has produced, moves at about 17 kilometers per second, and it required the gravitational assistance of multiple planetary flybys to reach that speed. The accumulated kinetic inheritance of Jupiter and Saturn's orbital momentum transferred to a small metal object through the geometry of close approach, against 550. This is the part where it would be easy to lurch toward hopelessness, toward some conclusion about permanent captivity, about the galaxy as a closed system from which nothing made by human hands will escape in any meaningful time. But that conclusion arrives too quickly, and it papers over something more interesting. The number 550 is not arbitrary. It isn't a rule imposed from outside. It emerges from the mass of the galaxy itself, from the trillion or so solar masses arranged across 100,000 light-years of disk and halo. Change the mass, and the number changes. Move closer to the center, where the mass density is higher, and the number rises. Move farther out, and it drops. Escape velocity is the galaxy's way of describing itself. It's the number the Milky Way produces when asked, "What would it take to leave me?" And here's the thing I keep circling back to, the thing that feels worth holding carefully, because I want to get it right rather than make it sound neater than it is. Escape velocity is defined entirely in terms of the object being escaped from, not the object leaving, not the destination, not the path taken. The number comes entirely from the mass and radius of the source. The thing you are leaving writes the exit condition. Your own properties, your mass, your composition, whether you are a spacecraft or a photon or a grain of interstellar dust, none of that enters the calculation. Escape velocity is the same for everything, regardless of what's doing the escaping. Which means the condition for leaving is authored entirely by what you're inside. There's a moment. It comes somewhere in the middle of thinking about this, where the logic folds back on itself in a way that's hard to describe without making it sound more mystical than it is. So let me try to be careful. To know whether you can leave, you need to know the escape velocity. To know the escape velocity, you need to know the mass of what you're inside. To know the mass, you need to understand the structure of what contains you. and the structure of what contains you is, at galactic scales, still only partially known. The dark matter distribution isn't mapped with precision. The total halo mass has meaningful error bars. The exact escape velocity is itself a range rather than a point. So the exit condition is defined by a thing that hasn't been fully measured. You are trying to calculate the cost of a door whose dimensions haven't been fully agreed upon. None of this is a paradox, it's just science operating at its actual edges rather than its textbook center. The escape velocity from the Milky Way is real. The number exists. The uncertainty around it is an epistemic problem, not a physical one. The galaxy has a specific mass whether or not we've measured it precisely, and that mass produces a specific escape velocity whether or not we've calculated it exactly. But there's something about the uncertainty that feels honest in a way that the clean version of the number doesn't. Now the metaphor. Or, not quite a metaphor, more an analogy that arrived sideways, and I haven't fully decided whether it holds. Think about trying to leave a conversation that hasn't ended. Not an argument, nothing charged. Just a long, slow, sprawling conversation with someone you've known a long time, in a room that's comfortable, at a time of night when the logical stopping points keep appearing and then passing without either of you taking them. You keep thinking, this is where I'd leave, and then another thread opens, and you're still there. The conversation hasn't trapped you. You could stand up at any point, but the conditions for leaving keep being defined by the conversation itself, by its current state, by what's just been said, by what feels unfinished. Every moment you calculate the exit, the thing you're trying to exit has already moved slightly, and the calculation updates. That's not quite what escape velocity is. Physically, it's simpler than that. It's a fixed number derived from fixed properties, not a moving target. But the feeling of it, the way the exit condition is authored by the interior of the thing you're inside, that's where the analogy snags and holds for a moment before releasing. Escape velocity also has nothing to say about whether leaving is desirable. It's a purely mechanical threshold. It doesn't weigh the reasons for going. It doesn't account for what's on the other side. It simply describes the energetic cost of departure, calculated from the gravitational depth you're currently occupying. The galaxy's exit price is 550 kilometers per second sustained. No commentary on whether you'd want to pay it. There's a specific detail worth adding here, because it sharpens the picture in a way that matters. Escape velocity applies to unpowered objects, things given an initial velocity and then left to coast. A rocket with continuous thrust operates differently. It doesn't need to reach escape velocity all at once if it can keep accelerating continuously, trading fuel for gradual increase in speed against the decreasing gravitational force as it moves outward. But even a continuously thrusting spacecraft faces the same underlying reality. The energy required is the same, the gravitational depth is the same. The continuous thrust just allows you to pay the energy cost in installments rather than all at once. The total bill is identical. The galaxy doesn't offer discounts for effort. The mass is what it is, 550 kilometers per second, or 500, or 600, depending on the dark matter. A speed that nothing built by human hands has come close to reaching. A speed that even the fastest natural objects in the galaxy, hypervelocity stars flung outward by interactions with the supermassive black hole at the galactic center, only just meet or barely exceed, and then only under the most extreme gravitational circumstances. The threshold for leaving is set by the same mass distribution that makes the galaxy what it is. Change the mass to lower the threshold, and you no longer have a galaxy of this size. The thing that traps you is the same thing that makes the structure real. Is that containment, or is it just what belonging looks like, expressed as physics? I don't know. I'm not sure the question has a clean answer. Or maybe it does, and the answer is simply both simultaneously, with neither cancelling the other out. The number exists, the physics is clear. What physics means for anything larger than itself is a different kind of question, the kind that doesn't resolve so much as settle, slowly, into the background of thinking, where it continues to do something without ever quite finishing, which, as thoughts go, is a reasonable place to leave it for now. The dark matter that inflates this exit price, that pushes the escape velocity from what visible matter alone would demand into the range it actually occupies, doesn't announce itself. It has no light to offer. It arrived in this story as a consequence, as a correction to a number that didn't add up, and that's mostly how it continues to appear, as an absence that leaves traces in everything around it. That absence is worth its own time. The shape of a thing that cannot be seen is its own kind of fact. Start at the outside and work inward. Not the outside of the galaxy, further than that, further even than the halo, out into the space between galaxy clusters where the density of everything drops to near nothing and the universe begins to show its largest structures, the ones that only become visible when you've retreated far enough that individual galaxies blur into points, and what remains is the pattern they form together, the filaments and voids, the cosmic web that astronomers map through the distribution of light and the inference of what lies between the light. Even out there at that remove, dark matter is doing structural work. The filaments of the cosmic web, the vast threads along which galaxies cluster, the scaffolding of the observable universe at its largest scale, are not primarily made of the gas and stars and dust that produce light. They are made in their dominant mass contribution of dark matter. The visible galaxies are, in a sense, tracers, bright points marking the intersections and threads of a much larger invisible architecture that assembled itself in the first few 100 million years after the Big Bang. When quantum fluctuations in the early universe's density, fluctuations so small they were measured in parts per 100,000, were amplified by gravity into the seeds of everything that followed. Dark matter collapsed first. The visible matter fell into the gravitational wells dark matter had already prepared. This is worth pausing on because it reorders the intuitive picture of how the universe came to look the way it does. The common mental image, gas clouds collapsing under gravity, stars forming, galaxies assembling, is correct but incomplete, and the incompleteness matters. The gas clouds didn't collapse into arbitrary locations, they collapsed into regions where dark matter had already been accumulating for millions of years, deepening the gravitational wells, providing the scaffolding into which ordinary matter could settle. Galaxies didn't form and then acquire dark matter halos. The halos formed first, or simultaneously at minimum, and the visible galaxy assembled within them. The Milky Way, then, is not a structure surrounded by a dark matter halo the way a pit has water in it. It's more that the halo is the primary structure, and what we call the galaxy, the disk of stars and gas that we image and map and think of as the Milky Way, is the luminous inner portion of something much larger, much more massive and almost entirely invisible. The stars are, in this framing, a kind of surface detail. The Milky Way's dark matter halo extends somewhere between 200,000 and 400,000 light-years from the galactic center, depending on the model, depending on how the edge of the halo is defined, and the edge of the halo has the same definitional softness that the edge of the stellar disk has, the same gradual thinning rather than clean termination, the same quality of ending without a clear ending point. The halo is not a shell with an interior and an exterior cleanly separated. It's a density distribution, dense near the center, and decreasing outward in a profile that astronomers describe with mathematical functions but that resists clean visualization. What the halo contains, in terms of mass, is roughly 5 times what the visible galaxy contains. 5 times the mass of every star, every gas cloud, every dust grain, every planet, every moon, every piece of rocky debris orbiting any star in the Milky Way. All of that multiplied by 5 is the contribution of the dark matter halo to the galaxy's total gravitational accounting. And none of it has been directly detected. This is the fact that takes the longest to fully absorb, and I find myself returning to it more than once while thinking about this, not because it's mysterious in an exciting way, though it is genuinely mysterious, but because it has a specific quality of wrongness that the mind keeps trying to smooth over by treating it as a technicality. It isn't a technicality. Dark matter is not undetected because we haven't built sensitive enough instruments yet, in the way that a faint star might be undetected because telescopes aren't powerful enough. Dark matter is undetected because it does not interact with electromagnetism. It doesn't emit photons. It doesn't absorb them. It doesn't reflect them. Every instrument that human science has ever used to observe the universe, every telescope, every radio dish, every X-ray detector, every infrared sensor, operates by collecting and analyzing electromagnetic radiation. Every image ever taken of the night sky is a map of electromagnetism. Dark matter is invisible to all of it, not faintly visible, not visible in some wavelengths and not others, invisible to the entire electromagnetic spectrum, from the longest radio waves to the shortest gamma rays. What we know about it comes entirely from its gravitational effects. The rotation curve of the Milky Way, the way orbital speed varies with distance from the galactic center, was the first robust evidence, and it remains among the clearest. In a system where mass is concentrated near the center, like a solar system, orbital speed should decrease with distance from the center. Planets farther from the Sun move more slowly, following Kepler's laws, because the gravitational influence they experience is weaker at greater distances. The outer planets are slower than the inner ones, and the pattern is mathematically predictable from the distribution of mass. The outer stars of the Milky Way don't follow this pattern. They orbit too fast, not slightly too fast, substantially too fast by factors that visible matter alone cannot explain. The rotation curve of the galaxy stays flat, or nearly flat, at distances where it should be declining, and this flatness persists across the disk and into the outskirts of the stellar population, maintained by the gravitational contribution of mass that isn't there, or rather, mass that's there but cannot be seen. Vera Rubin and Kent Ford documented this in the 1970s with systematic precision, observing galaxy after galaxy, finding the same stubborn flatness in the rotation curves of all of them, the same quiet refusal of the visible matter to account for the observed dynamics. The universe had been holding its shape with invisible hands all along. There are alternative explanations. Modified gravity theories, MOND, and its relativistic extensions, propose that gravity itself behaves differently at very low accelerations, in ways that could reproduce the observed rotation curves without invoking unseen mass. These approaches have genuine advocates, careful researchers who find the dark matter hypothesis unsatisfying and who have developed quantitative alternatives with real predictive power. But alternatives struggle with evidence that dark matter handles more gracefully, and the most significant piece of that evidence is the Bullet Cluster, 2 galaxy clusters that collided and passed through each other roughly 150 million years ago. When they collided, the hot gas, which comprises most of the ordinary mass in a galaxy cluster, interacted electromagnetically and was slowed and separated from the galaxies and dark matter, which passed through relatively unimpeded. Observations of the aftermath show the mass distribution, inferred from gravitational lensing, offset from the X-ray emission of the gas. The mass is where the dark matter should be. The gas is somewhere else. It's close to a direct image of dark matter's gravitational presence, separated from the ordinary matter it usually accompanies, and it's difficult, not impossible, but genuinely difficult, to explain through modified gravity alone. What dark matter actually is remains unknown. Not provisionally unknown, not unknown pending the next detector generation. Genuinely deeply unknown, in the sense that the range of viable candidate particles spans many orders of magnitude in mass. From ultralight axions massing less than a billionth of an electron's mass to hypothetical massive particles thousands of times heavier than a proton, and experiments sensitive across this range have not found a detection. The particle, if it is a particle, if there is one particle responsible rather than a family of them, if the dark matter problem is solved by a single addition to the standard model rather than something stranger, remains after decades of dedicated searches in underground laboratories shielded from cosmic rays, in collider experiments, in astrophysical observations, unidentified. The shape of the galaxy is being maintained by something whose fundamental nature is, at this moment, unknown. Come back inward now, from the large-scale structure, from the bullet cluster, from the rotation curves and the halo models, back to the Milky Way, back to the disk, back to the Sun's position at 26,000 light-years from center. The dark matter halo surrounding this position is not uniform. It has structure, over densities and streams, the remnants of smaller halos that were absorbed when the Milky Way merged with smaller galaxies over its lifetime, now tidally disrupted and stretched into long-arcing streams of dark matter orbiting through the halo's volume. The halo has a history written in its substructure, a record of the galaxy's growth through absorption, and this substructure is mapped, imperfectly, indirectly, through the gravitational influence of the streams on the motions of stars. The invisible is known through what it does to the visible, always. There is a philosophical register this could easily slide into, something about presence without evidence, about influence without observation, about the nature of knowing something you cannot see, and I want to stay careful about that slide, because the physics doesn't need it. The physics is strange enough on its own terms. An invisible component comprising the majority of the galaxy's mass, known only through its gravitational effects of unknown particle composition, extending far beyond the visible structure it surrounds, responsible for the galaxy's stability, the flatness of its rotation curve, the outcome of its formation. This is what the evidence describes. The strangeness is in the science. The philosophy for once is just a reflection of the fact. And here is the consequence that matters most for this larger story, the thing about never leaving. The escape velocity calculated in the last chapter, the 550 or so kilometers per second required to leave the Milky Way, is not primarily set by the stars. It isn't primarily set by the gas or the dust or the visible matter that makes up the bright, imageable galaxy. It is primarily set by the dark matter halo, the invisible extended structure that contains and surrounds everything else. Without the halo, escape would be easier. Not easy, but easier. The visible galaxy alone would impose a lower gravitational barrier. The thing making departure hardest is the thing you cannot see, which means, and this feels important enough to say plainly even at the risk of stating the obvious, that your confinement within the Milky Way is, in its majority contribution, a consequence of something whose existence was only inferred in the last 50 years, and whose nature remains unresolved. You are held here by the unknown, not metaphorically, not in a loose rhetorical gesture toward mystery. Literally, the dominant gravitational force keeping every star in this galaxy, including the Sun in its orbit, is produced by matter of unknown composition that has never been directly detected and may not be detectable with any instrument operating on electromagnetic principles. The galaxy is mostly made of something we don't understand, and that something is mostly responsible for the fact that you cannot leave. I'm not sure what to do with that, honestly. It doesn't frighten me, or maybe it does, mildly, in the way that genuinely open questions carry a faint charge of vertigo rather than dread. But it also feels like the galaxy is being honest about something, like the universe, at the scale where these questions become unavoidable, keeps producing the same answer to questions about its fundamental composition. More is unknown than known, and the unknown is load-bearing. The Milky Way's shape is held by something invisible. Its rotation is maintained by something we can't directly touch. Its history and future are largely written by a component whose identity remains an open scientific question after half a century of dedicated searching. And yet the shape persists, the rotation continues. The galaxy is, by any measure, stable over timescales that dwarf everything human civilization has existed long enough to imagine. The unknown is apparently very good at its job. There's a next layer to this. Not the halo, not the dark matter, but the visible architecture, the structure of the galaxy we can actually map. The disk seen from inside by instruments that can only look along the plane they're embedded in. What it's like to know a shape you've never seen from outside is its own kind of question, and it leads somewhere unexpected. Think about a house you knew well enough that you stopped seeing it. Not a house you visited, one you lived in long enough that the specific angle of light through a particular window in the late afternoon became invisible to you, became just afternoon, became just the room being the room. The way a smell disappears after 20 minutes of continuous exposure because the olfactory system, finding nothing new to report, quietly stops reporting. The way familiarity is, in a very literal neurological sense, a kind of blindness. You knew the house, you could describe it. You could navigate it in complete darkness, could reach for a light switch without thinking, could walk its hallways with your eyes somewhere else entirely. But you could not see it. Not really. Not the way someone entering for the first time would see it, taking in the proportions, the wear on the floorboards, the specific way the ceiling height changes between rooms. To really see a house, you need to not live in it. We live in the Milky Way. The galaxy's shape, spiral, barred spiral to be more precise, with a central bar structure from which the spiral arms extend, is not something any human instrument has ever observed directly from outside. Every image of the Milky Way that presents it as a sweeping face-on spiral is a reconstruction, a model, an educated inference assembled from data collected inside the structure, projected outward through calculation and comparison with other galaxies whose shapes we can see because we're not inside them. We know we're in a spiral galaxy the way you might know the layout of a city you grew up in. Not by having seen its aerial photograph, but by having walked its streets long enough that the pattern emerged from the accumulation of local knowledge. Except the streets here are light years long, and walking them takes longer than civilization has existed. What we actually have is this. We have stellar positions, the locations of stars mapped through parallax, through spectroscopic distance estimates, through the motion of masses in star-forming regions, through surveys like Gaia that have measured the positions and velocities of over 1 billion stars with extraordinary precision. We have the distribution of gas, traced through radio emissions from neutral hydrogen at the 21 centimeter wavelength that passes through the galaxy's dust unobstructed, giving us a map of where the gas is and how fast it's moving. We have infrared observations that penetrate the dust clouds obscuring the galactic center in visible light, revealing the dense stellar populations of the bulge and the structure of the central bar. From all of this, from the accumulated inference of a century of observational astronomy, we've assembled a picture. The Milky Way has 4 major spiral arms, or possibly 2 major arms with secondary features, depending on how the evidence is weighted and which traces are trusted most. The uncertainty is real. The arms are named: Sagittarius, Perseus, Norma, Scutum Centaurus. The Sun sits between the Sagittarius and Perseus arms in a smaller partial structure called the Orion arm, or the Orion spur, a minor feature, a branch off one of the larger arms rather than a primary arm itself. We are, in architectural terms, in the corridor between the main rooms. The central bar is roughly 27,000 light-years long, oriented at an angle to our line of sight, connecting the origins of the spiral arms and surrounding a dense nuclear region where star formation rates are high and the gravitational environment is extreme. At the very center, actually, at the center, within a region a few light-years across, is Sagittarius. A star, the supermassive black hole, with a mass of approximately 4 million suns, its presence inferred for decades from the orbits of stars moving around an invisible point of enormous mass, and now imaged directly by the Event Horizon Telescope in 2022, a blurred orange ring of heated matter at the threshold of a thing from which nothing returns. That's the center. And from here, from the Orion spur at 26,000 light-years out, it sits below the southern horizon at certain times of year. A direction rather than a visible point. A region of the sky where the stellar density increases and the dust clouds thicken, and somewhere behind all of it, the black hole does its quiet, ancient, unobservable work. Here's the thing about being inside the spiral. Gaia, the European Space Agency astrometry mission that has been mapping stellar positions and velocities since 2014, has produced something that comes closer than anything before it to a view of the Milky Way's local structure from a God's eye perspective, not because it transcended the inside problem, but because it solved a different version of it. By measuring the 3-dimensional positions and the full 6-dimensional phase space, position plus velocity in all 3 dimensions, of over 1 billion stars, Gaia has produced a map rich enough that the structure of the Orion arm, the warp of the galactic disk, the streams of stars from disrupted dwarf galaxies, and even the ghost of the Milky Way's merger history are readable in the data. Not an image from outside, still an inference from inside, but an inference of such density and precision that the distinction begins to matter less. Still, the full face-on view, the image that would show the complete spiral, the bar, the arms in their entirety, the overall proportions of the structure, remains unavailable. We're still in the house. What that means, practically, is that the map of our galaxy is permanently the least detailed map of all the galaxies we study well. The Andromeda galaxy, 2.5 million light-years away, gravitationally bound to the Milky Way approaching us at roughly 110 kilometers per second, can be imaged as a complete structure. Its spiral arms, its central bulge, its satellite galaxies and stellar streams can all be photographed in a single exposure. We see all of Andromeda and none of the Milky Way. This is not, and I want to be careful here, because it would be easy to misstate. This is not a deficiency of the Milky Way. It isn't less knowable in any absolute sense. It's differently knowable. It's a galaxy we know from the inside with the specific kinds of knowledge that interiority makes possible and the specific blindnesses that interiority imposes. We know the sun's velocity relative to the local standard of rest to extraordinary precision. We know the distance to the galactic center to within a few percent. We know the composition of the interstellar medium in our local neighborhood with a granularity that observations of other galaxies could never provide. These are things you can only know by being there. What we can't do is step back. The house again, the one you knew well enough to stop seeing. You knew where the cold spots were in winter, the drafty corner of the bedroom, the hallway that never quite warmed up no matter what. You knew which floorboard creaked third from the top of the stairs. You knew the specific smell of it after rain, something mossy in particular that you couldn't have described from memory but would have recognized instantly. None of that knowledge is available to the person who photographs it from the street. They have the proportions, the roofline, the relationship of windows to walls, the overall structure, the shape. They don't know the cold corner. We know the cold corner of the Milky Way. We know our specific address within it, our velocity through it, the history written in the local stellar populations around us, the age and composition of our nearest neighbours. We have a kind of knowledge of this galaxy that is genuinely unavailable to any observer positioned outside it. It's just a different kind of knowledge than a photograph provides. And there are things a photograph would show that we will never be able to see. This insideness, is it a limitation, or is it just the condition? I keep coming back to that question without quite landing on an answer, which probably means it's the wrong kind of question, the kind that feels like it's asking for a verdict when the actual situation is more like a texture. Being inside the Milky Way isn't good or bad epistemically. It's a set of trade-offs that can't be escaped because they're structural, because the observer is part of the system being observed, and there's no position outside the system available, and there never will be, not in any timeline that connects to human existence. All maps of the Milky Way are maps made from the inside. All knowledge of this galaxy is knowledge built by instruments embedded in the thing they're studying. And yet the knowledge is real. The structure has been traced. The arms have been named. The bar has been measured. The black hole imaged. The warp of the disk quantified. The merger history reconstructed from the streams of disrupted dwarf galaxies still arcing through the halo. You can know a house without ever having seen it from outside. You just know it differently. And what surrounds the house, the neighborhood, the wider street plan, the other structures we're gravitationally bound to, that's something else again. The Milky Way is not alone. It moves through space as part of a larger assembly of galaxies, loosely gravitationally bound, moving together, and in relation to one another in ways that carry their own kind of vertigo when you sit with them long enough. That's the next part of the picture, the neighborhood and where it's going. There's an instinct, understandable, almost automatic, to find relief in zooming out. The idea that scale brings perspective and perspective brings peace. That if the things pressing on you could be made small enough by comparison, they'd lose their weight. It's an instinct that works sometimes in certain registers of trouble. Personal difficulties, set against geological time or stellar distance, do sometimes thin and quiet. The trick works. The local group doesn't offer this. The local group is the gravitationally bound collection of galaxies to which the Milky Way belongs. It has no sharp boundary. Membership is assessed gravitationally by whether a galaxy is bound to the group's combined mass or drifting free from it on the general expansion of the universe. It contains somewhere between 80 and 100 galaxies depending on the survey, most of them small, most of them satellites of either the Milky Way or Andromeda, the two dominant members. Its total diameter is roughly 10 million light-years, give or take. An irregular volume of space with no clean center and no clean edge, just a region where galaxies are gravitationally associated with each other, rather than being swept apart by cosmic expansion. The Milky Way and Andromeda together contain the overwhelming majority of the local group's stellar mass. The remaining members, the Triangulum Galaxy, the Magellanic Clouds, dozens of dwarf spheroidals and irregulars with names like Sculptor, Fornax, Carina, Leo I, orbit the two large galaxies or drift through the group's volume in more complex paths shaped by the combined gravitational influence of everything else. This is the neighbourhood. This is as local as it gets at galactic scales. The Magellanic Clouds are worth a moment's pause here, because they're the local group members most accessible to the naked eye, visible from the southern hemisphere as detached patches of the Milky Way, luminous enough to cast faint shadows on very dark nights, close enough that their internal structures are resolvable in detail. The large Magellanic Cloud sits about 160,000 light-years away. The small Magellanic Cloud, roughly 200,000 light-years. Both are irregular dwarf galaxies, distorted by tidal interactions with the Milky Way into shapes that have lost whatever spiral or elliptical order they might once have had. The Milky Way has been pulling at them, and they at it, for billions of years. And the record of this interaction is written in the Magellanic Stream, an arc of gas stretching across hundreds of degrees of sky, drawn out from the clouds by tidal forces over hundreds of millions of years, slowly falling toward the Milky Way's disk. The Milky Way is in the process of consuming them, slowly, over timescales that make process feel like the wrong word for something this patient and this enormous. Andromeda is different in kind rather than degree, not a satellite, not a subordinate member. A peer, larger than the Milky Way by most estimates, containing perhaps 1 trillion stars to the Milky Way's several hundred billion, sitting at a distance of approximately 2.537 million light-years and approaching at roughly 110 kilometers per second. Approaching directly. The Milky Way and Andromeda are falling toward each other, not because anything is pushing them together, but because their combined mass is sufficient to overcome the local expansion of the universe between them, the general tendency of space to carry unbound objects apart, which operates everywhere but can be locally reversed by sufficient gravitational attraction. The two galaxies are bound, have always been bound, and are, over the span of the universe's current age, completing the first gravitational arc of an eventual merger. In approximately 4.5 billion years, give or take several hundred million, the uncertainty reflecting genuine complexity in the models, Andromeda will pass through the Milky Way. That sentence deserves its own pause, not collision in the sense of two solid objects striking each other. Galaxies are extraordinarily empty at the scale of their constituent stars. The average distance between stars in the galactic disk is several light-years, and two interpenetrating disks of stars will pass through each other with vanishingly few actual stellar collisions, the stars threading between one another like two overlapping swarms occupying the same space without their members touching. But the gas clouds will collide. Gas is spatially extended and interactive in ways that stars aren't, and when two galaxies merge, their interstellar medium collides and compresses, triggering enormous bursts of star formation, starbursts that briefly make the merging system one of the most luminous objects in its region of the universe. And the gravitational dynamics will reshape both galaxies completely, destroying the disk structures of both, pulling stars into long tidal streams, producing a chaotic, regular combined structure that will eventually settle over billions of years of dynamical relaxation into a large elliptical galaxy. The working name for this future object is Milkomeda, or sometimes Milkdromeda. Neither name has any official status. They're placeholders for a thing that doesn't exist yet and won't for a time span 4 times longer than the current age of the Earth. But the local group's motion isn't only about Andromeda. The group itself is moving, not just expanding, moving with a coherent bulk velocity in a specific direction at a specific speed relative to the cosmic microwave background. The local group is being pulled, along with thousands of other galaxies across a region hundreds of millions of light-years wide, toward a massive concentration of matter in the direction of the constellation Centaurus. This concentration is called the Great Attractor, and here is where the zooming out stops providing comfort, if it ever was going to. The Great Attractor is an overdensity, a region of space with significantly higher mass than average, whose gravitational pull is detectable in the systematic motions of galaxies across a vast surrounding volume. The local group is moving toward it at roughly 600 kilometers per second. Most of the galaxies in our cosmological neighborhood, the local supercluster, the broader region that includes thousands of galaxy groups and clusters, share this motion, all of them streaming in the same direction, all of them drawn toward the same concentration. What is the Great Attractor exactly? This is where the answer gets harder to give cleanly. The Great Attractor sits behind the zone of avoidance, the region of sky obscured by the dust and gas of the Milky Way's own disk, which blocks optical observations of roughly 20% of the sky. For decades, the Great Attractor was an inferred presence, its existence deduced from the streaming motions of galaxies without any direct imaging of the mass responsible. Radio and X-ray observations, which penetrate the dust more effectively than optical light, have since identified the Norma cluster, a dense galaxy cluster, near the center of the Great Attractor region. But subsequent surveys have complicated the picture. The streaming motions extend beyond the Great Attractor itself, suggesting it may be part of a still larger structure. The Shapley supercluster, one of the most massive concentrations of matter in the observable universe, located roughly 650 million light-years away. We might not be falling into the Great Attractor so much as falling through it, towards something larger still. The thing that I find difficult to hold isn't the scale exactly. Scale, past a certain point, becomes a kind of abstraction that the mind accepts without really registering. 650 million light-years and 65 million light-years both feel roughly like very far, in the same way that very large numbers of anything past a few thousand stop conveying different qualia of size. What I find difficult, and I'm not sure difficult is quite the right word, maybe textured is closer, is the quality of the motion. We are moving toward a thing we only partially understand as part of a stream of thousands of galaxies all moving together. And this motion is old. It's been happening since structure formed in the early universe, since the initial overdensities that would become the Great Attractor began drawing in surrounding matter, and it will continue regardless. The streaming motion isn't something that started recently and might stop. It's the universe's large-scale gravitational dynamics expressing themselves over cosmic time, and the local group is inside those dynamics, carried by them. There's no standing still at these scales. There's only which flow you're in, which is perhaps the particular flavor of vertigo the local group produces that smaller scales don't. Personal difficulties can be set against geological time and diminished. The galaxy's size can be contemplated, and the smallness it produces can carry a certain lightness. But the local group, moving as a coherent structure toward a gravitational concentration large enough to organize the motion of thousands of galaxies, this doesn't make things feel smaller. It makes them feel embedded, carried, part of a flow that was already moving before anything alive existed to notice it. Not trapped in a cage. Something quieter than that. Caught in a current. inside a motion so large and so old that inside becomes the only honest description of the relationship, the local group will survive. Over the long timescales of the universe, the gravitationally bound members will remain associated even as the rest of the universe, the galaxy clusters not bound to any local structure, recedes on the expansion of space, redshifting into invisibility over trillions of years as the accelerating expansion carries them beyond the observable horizon. The local group will be, eventually, the entirety of the observable universe for any civilization that exists within it. Every galaxy not gravitationally bound will have receded beyond the point where light can reach from them in finite time, but that's later, much later. For now, the group moves together, held by its own gravity, drawn by a larger gravity still, inside a flow that extends across hundreds of millions of light years and has been running for billions of years. And somewhere inside all of this motion, one specific star, one specific planet, the specific weight of a body in a room is doing its own quiet orbiting. The speeds involved in all of this are not felt, not by the body, not by any instrument sensitive to human scale experience. You are embedded in bulk motions ranging from the Sun's 220 km per second orbit around the galactic center to the local group's 600 km per second streaming toward the great attractor, and none of it produces a sensation. No wind, no pressure, no sense of direction. The body doesn't know it's in a current. But the mathematics of the current is real, and the current is running, and it has been running for longer than the sun has existed. There's a specific fact that this chapter keeps circling around without quite landing on, and it's the fact about speed. Not the galaxy's orbital speed, and not the local group's streaming velocity toward the great attractor, but the number that emerges when you add up all of the velocities a body on Earth is simultaneously participating in. Earth's rotation, Earth's orbital velocity around the Sun, the Sun's motion relative to the local standard of rest, the Sun's orbit around the galactic center, the Milky Way's motion within the local group's streaming motion toward the great attractor, added vectorially, accounting for directions, not just magnitudes. The number that emerges is somewhere around 600 kilometers per second, relative to the cosmic microwave background, the most uniform reference frame available. 600 kilometers per second, roughly, in a room that reports nothing. That number, it's worth carrying into the next thought. Not as a cause for anything, not as a problem to solve, just as a fact about what stillness means from inside a system that has never, not once, been still. The sun is moving through space at a speed that would carry it from Earth to the moon in about 20 minutes. It has been moving this way for 4.6 billion years, and will continue for roughly the same again. And this is the slow component, the local one, the orbital motion around a galaxy that is itself carried in a stream toward a gravitational concentration that may itself be part of a still larger flow. Still. The room reports nothing, which is either the strangest thing about the universe or the most ordinary. Probably both, which is maybe why it keeps coming back, not answered, just persistent the way certain facts are. The number first, not explained yet, just placed here at the start where it can sit without context for a moment. 600 kilometers per second, that's the approximate speed of the solar system relative to the cosmic microwave background, the faint thermal radiation left over from the early universe, filling all of space, representing the closest thing physics has to a universal reference frame. When you account for every layered motion the solar system participates in, Earth's orbit around the Sun, the Sun's orbit around the galactic center, the Milky Way's motion within the local group's streaming toward the great attractor, and add them up as vectors, accounting for their directions as well as their magnitudes, 600 kilometers per second is roughly what emerges. The title of this chapter uses miles per second because the number is cleaner that way. 373 miles per second, close enough. And the unit doesn't matter. What matters is the quantity it's describing and what that quantity exists inside of. 600 kilometers per second is fast. Faster than any spacecraft ever built. Faster than the fastest natural projectiles in the solar system. Fast enough that in the time it takes to blink, a genuine blink, the kind the nervous system produces involuntarily, somewhere between 150 and 400 milliseconds, the solar system moves between 90 and 240 kilometers through space. During a blink, and the body reports nothing, no pressure against the front of the face, no sensation of air resistance, which is irrelevant in the vacuum of space but which the physical intuition reaches for anyway, trying to construct a feeling for the speed and finding no purchase. No sound, no vibration, no instrument in the human nervous system capable of detecting any of it. The vestibular system, the balance and motion sensing apparatus of the inner ear, responds to acceleration, to changes in velocity, not to velocity itself. Constant motion at any speed is indistinguishable from rest. If the motion is truly constant and truly uniform, this is Galilean relativity, 4 centuries old, intuitive once grasped. A person in the smooth cabin of a ship moving at constant speed across calm water cannot, without looking outside, tell whether the ship is moving or docked. The physics of the interior is identical in both cases. The solar system's motion is not perfectly constant. There are small accelerations, perturbations, the very slight gravitational tugs of passing masses. But at human timescales and human sensory thresholds, it is constant enough that the difference is irrelevant. 600 kilometers per second, indistinguishable from zero. There's a specific quality to this fact that separates it from other large number astronomy facts. Most large number astronomy facts are large in a way that simply escapes intuition. The distance to the Andromeda galaxy, 2.5 million light-years, is not something the mind can hold as a felt quantity. It becomes a symbol for very far. The mass of the Sun in kilograms is a number so large that it functions more as a category, unimaginably massive, than as a specific quantity. The largeness just accumulates beyond a threshold, and past that threshold the specific value stops mattering to the nervous system, which has no reference experience to attach it to. 600 kilometers per second is different. Not because the mind can genuinely grasp it, it can't, not really, but because the mind can grasp what's being claimed about it. The claim isn't that a number is large. The claim is that something is happening right now that your body cannot feel. That's a different kind of statement. It's not about magnitude. It's about the relationship between reality and experience. The Earth orbits the Sun at approximately 30 kilometers per second. This component alone, just the Earth's orbital velocity, the smallest significant contributor to the total, means that in 1 minute the Earth has moved 1,800 kilometers from where it was. In the hour it might take to fall fully asleep, it will have moved 108,000 kilometers. That's roughly a third of the distance to the Moon, travelled while lying still undetected, the body at rest in the familiar sense while also in motion in this other sense that the body has no access to. The Sun, carrying the Earth along with it, orbits the galactic centre at about 220 kilometers per second. This is the largest well-constrained component. One orbit takes approximately 225 million years. The Sun has completed roughly 20 of these orbits in its lifetime. 20 galactic years, a unit sometimes called a cosmic year, each one spanning the rise and fall of entire geological periods on Earth. The last time the Sun was in this position in its orbit, The Triassic period had not yet begun. Dinosaurs didn't exist. The land masses of Earth were configured differently. The atmosphere had a different composition. The Sun returned to roughly this position after 225 million years of orbiting, and found a planet with humans on it, one of whom is lying somewhere reading about the fact. Add the Milky Way's motion relative to the local group's centre of mass, roughly 40 to 50 kilometers per second, direction roughly toward the constellation Leo. Add the local group's bulk streaming velocity toward the great attractor, somewhere around 600 kilometers per second, though this number carries more uncertainty than the galactic orbital velocity, because bulk flows at this scale are harder to measure cleanly. These vectors don't all point the same direction. They partially cancel, partially reinforce depending on the specific geometry at any given moment. The total measured against the CMB comes out near 600 kilometers per second, currently directed, the solar system's motion, roughly toward the constellation crater in the southern hemisphere sky, toward crater, at 600 kilometers per second, every second of every day, silently, without sensation, while people sleep, while people argue, while seasons change and governments form and collapse and form again. The direction barely registers as a fact. It's almost comic, the specificity of it, toward crater specifically, as if the universe had filed a flight plan. But the specificity is real, the motion is real, the constellation is just a way of pointing us direction in space, and the direction is measured, and the measurement is this. The cosmic microwave background deserves a moment here, because it's doing something important in this accounting. The CMB is the thermal radiation produced when the early universe cooled enough for electrons and protons to combine into neutral hydrogen approximately 380,000 years after the Big Bang, releasing photons that have been travelling freely ever since, redshifted by the universe's expansion from the temperatures of a glowing plasma to the microwave frequencies detected today, corresponding to a temperature of about 2.725 Kelvin. It fills all of space. Every point in the observable universe is bathed in it equally, arriving from all directions, the afterglow of the universe's hot early state, and it's very nearly perfectly uniform. Variations across its temperature exist but are tiny, on the order of 1 part in 100,000, and carry enormous scientific importance as the seeds of all subsequent structure. But for the purpose of this chapter, what matters is the uniformity. Because the uniformity means that any deviation from uniformity is informative, any direction from which the CMB appears slightly hotter, slightly bluer, blue shifted by the Doppler effector, indicates motion towards that direction. Any direction from which it appears slightly cooler indicates motion away. The CMB is a speedometer for the universe, not for objects moving within it, for the reference frame itself, and the solar system's motion through it is measured 600 kilometers per second toward crater, toward a large-scale flow that has been running since the universe was young. What does stillness mean then? Not rhetorically, as a genuine question about what the word is doing when it's used. The body feels still. The room is still, not perfectly. There are small vibrations from the building, from traffic outside if there is any, from the HVAC system, cycling on somewhere in the structure. A low mechanical hum that becomes part of the room's ambient texture and stops being noticed. But still in the sense that matters for rest. Still enough. Still in the way that allows the nervous system to begin its overnight work, the consolidation of memory, the repair of tissue, the slow cycling of sleep phases. That stillness is real. It isn't an illusion that 600 kilometers per second exposes as false. The velocity doesn't unmask anything. The two conditions, bodily stillness and cosmological motion, are genuinely simultaneous, genuinely compatible, not in tension. Stillness at human scale, motion at cosmic scale, same body, same moment, both true. This coexistence of states, rest and motion, stillness and velocity, the body's experience and the physics of the system it's embedded in, doesn't resolve into a single cleaner truth. It isn't the case that the motion is the deeper reality and the stillness is illusory, or that the experienced stillness is what matters and the cosmological velocity is an abstraction without experiential weight. They're both fully real. They operate at different scales, different reference frames, different levels of description of the same situation. Physics has a word for this general situation. It isn't one word, actually. It's a set of ideas about reference frames and the relativity of motion and the principle that physical laws operate identically in all inertial frames. But the lived version of it, the version available without equations, is just this. The body in a room at rest and the solar system hurtling through space at 600 kilometers per second are not contradictory descriptions. They are descriptions at different levels of the same layered situation. The body doesn't need to resolve this. It can hold both and continue resting. 600 kilometers per second, silently right now, in the direction of crater inside a flow that doesn't care about the direction it's named for, toward a gravitational concentration that may itself be part of something larger still. The room hums with whatever machine is doing its overnight work. The weight of the body presses into whatever is holding it. Outside, depending on cloud cover, the light from stars that are also moving, all of them, all 400 billion in the galaxy, each with its own velocity vector, each following its own curved path through the gravitational geometry the galaxy has produced, may or may not be visible. The number was placed at the beginning of this chapter without context. Now it has context, and the context doesn't make it easier to hold, doesn't make it smaller or larger, doesn't change what it is, but it places it properly, not as a cause for alarm, not as a source of wonder that needs to be performed, just as a fact about the conditions under which rest occurs. The stillness is real, the velocity is real, both are true, and neither cancels the other. What the velocity is moving through, the large-scale structure of the universe, the flows within flows, is one side of this. The other side is what the velocity says about the nature of the container, the galaxy, the local group, the larger web of gravity that shapes all of this motion. None of these structures are permanent. The stability that makes the word structure feel appropriate is a stability on human timescales, or even stellar timescales. On longer timescales, what looks like a stable container is in motion, in evolution, in the slow process of becoming something different. That is somewhere ahead. Begin somewhere you can't quite reach. 4.5 billion years from now, give or take several hundred million, the models carry genuine uncertainty, and the uncertainty is honest rather than evasive. The night sky, from whatever remains of Earth, will look nothing like it does tonight. Andromeda will have grown over the preceding billions of years from a faint smear in the direction of Perseus to something enormous, something that fills a significant arc of sky, its spiral structure visible to the naked eye if there are eyes, its light mixing with the light of the Milky Way in ways that make the boundary between the two galaxies increasingly difficult to locate. And then the boundary will stop being a useful concept entirely. The merger won't announce itself with a single dramatic moment. That's worth saying early, before the mind reaches for the image of a collision, because collision implies a before and after, an impact, a discrete event in time. Galactic mergers are different in character. They are processes drawn out over hundreds of millions of years, and the stages of the process are themselves so extended that no observer living inside them would have the temporal vantage to see the whole arc. What would be seen over the millions of years of the merger's most active phase is a sky in progressive transformation. The familiar constellations, already shifted beyond recognition by stellar proper motions over the billions of years leading up to this, replaced by configurations shaped by the combined stellar populations of two galaxies interpenetrating, the tidal forces pulling stars into long luminous streams arcing across the sky, the galactic centre of Andromeda approaching and then passing and then receding, and then approaching again through the first few oscillations of the merger, the two systems swinging through each other in diminishing passes until dynamical friction bleeds away the relative momentum and the combined structure settles toward a single gravitational centre. The eventual product will be an elliptical galaxy, roughly spheroidal, supported by the random orbital motions of its stars rather than the ordered rotation of a disk, less structured in appearance than either of the spirals it formed from, and very likely, this is the part worth pausing on, very likely containing the Sun somewhere inside it. If the Sun still exists, it will for a while. The Sun's main sequence lifetime is approximately 10 billion years, and it's currently 4.6 billion years old, which gives it roughly 5 billion years before it exhausts its core hydrogen and expands into a red giant, consuming the inner planets. The merger arrives within that window, barely. The Sun will be old by then, swelling toward its end stages, but probably still present in some form when the two galaxies first pass through each other. Which means the solar system, if it survives the merger's tidal disruptions, will remain inside a galaxy. A different galaxy, shaped differently, named differently if named at all, but a gravitationally bound structure containing the Sun's mass, or what remains of it, along with the stars of two former spirals now combined into one elliptical. The merger doesn't liberate the solar system, it transforms the container. And this is where the word leave starts to behave strangely, starts to lose the clean applicability it seemed to have at the beginning of this whole inquiry. What does it mean to leave a galaxy if the galaxy merges with another galaxy, and the merged structure contains you? You didn't leave, but the thing you were inside changed shape completely, changed its stellar population, its dynamics, its morphology, its name. The Milky Way, as a discrete recognizable structure, will cease to exist. So in some sense the Milky Way will be left, not by the solar system departing, but by the Milky Way itself dissolving into something larger. The container leaves you, rather than you leaving the container. No, wait, that's not quite right either, because the container doesn't leave anything. It transforms, it merges. The stars of the Milky Way will still exist inside Milkomeda. They'll have new orbital parameters, new neighbours, new trajectories through a gravitational potential that is now the combined product of 2 trillion solar masses rather than one. But they'll still be there, still bound, still inside. The word leave keeps finding itself without a clean referent. This isn't a wordplay problem. It's pointing at something real about the nature of galactic structures and what it means to be inside them. The Milky Way isn't a physical container with walls. It's a gravitationally bound configuration of matter, a pattern almost imposed on a distribution of mass by the interplay of angular momentum, gravity, and the initial conditions of its formation. The pattern is stable on the timescales of stellar lifetimes. It has persisted for most of the universe's current age, but it isn't permanent in the way a bowl is permanent, a bounded thing that either contains you or doesn't. It's more like, and I'm going to try this analogy carefully, because it either lands or it doesn't. It's more like a weather system, a specific identifiable configuration of matter in motion, coherent enough to be named, persistent enough to have a history, real enough to have measurable effects on everything inside it, and yet not a thing in the way a rock is a thing, not something with an interior that's categorically different from an exterior, a pattern in a medium with edges that are themselves part of the pattern. And weather systems don't contain their contents. They are their contents for a while. The universe, at scales beyond the local group, is indifferent to these categories in a more fundamental way still. On cosmological scales, the scales at which the universe's expansion is the dominant dynamics, the concept of inside a galaxy is already a local description, applicable only within a gravitationally bound structure, where the expansion has been locally reversed by the structure's own gravity. Outside such structures, the expansion of space itself carries matter apart at rates that increase with distance, carrying unbound galaxies beyond each other's observable horizons over timescales of tens of billions of years. The universe doesn't organize itself around the concept of departure. There is no cosmic coordinate system in which leaving is a well-defined action. There are gravitationally bound systems in which objects remain associated, and there is the expansion carrying unbound objects apart. Neither of these is leaving in any meaningful sense. They're just the two modes of large-scale motion that the universe operates in. Here's what I find genuinely interesting about this, and it's not a performed interest. It's the kind of thing that actually snags attention when the thought is followed carefully enough. The word leave contains an assumption that there is a clearly bounded place, a self capable of departing, and a moment of departure that can be identified. In everyday experience, these conditions are usually met. You leave a room, a building, a city, the boundary is clear, the moment is identifiable, the place being left has a coherent identity that persists after you've gone. At galactic scales, each of these assumptions degrades. The boundary of the Milky Way, as earlier chapters have explored, isn't a clean line. It's a gradient of density, a statistical transition from inside to outside that depends on what you're measuring and resists precise location. The self doing the leaving, the solar system, the Earth, a human body, is itself inside multiple nested gravitational structures simultaneously. The solar system, the Milky Way's disk, the dark matter halo, the local group, the local supercluster, the larger flows toward the greater tractor. Which of these is the thing being left? The moment of departure has no clear definition, because the escape velocity threshold, as explored earlier, isn't a line you cross with a bang. It's an energy condition that, if met, means you asymptotically coast away without ever reaching zero speed or zero gravitational influence. Leaving falls apart quietly when applied to a galaxy, not because the physics is unclear, but because the word was built for a different scale of experience. There's a specific concept in cosmology that illuminates this from a different angle, the idea of gravitational binding. Two objects are gravitationally bound if their total mechanical energy, kinetic energy plus gravitational potential energy, is negative. Negative total energy means the object doesn't have enough kinetic energy to escape the gravitational potential while it's in. It will eventually return regardless of how far it travels because the gravitational potential energy is always large enough to decelerate it to rest before it reaches infinity. The solar system's total mechanical energy relative to the Milky Way is negative. It is bound. This isn't a provisional condition or a temporary state. It's a description of the current energy accounting, and it would require an enormous impulsive addition of kinetic energy to change. But bound isn't the same as contained. The word contained suggests passivity, enclosure, a thing held against its will or against its tendency. Bound is a statement about energy. It's a physical accounting. The solar system orbits the galactic center not because it's trapped, but because it doesn't have enough energy to do otherwise. And this is the same description applied to different numbers as why the Earth orbits the Sun and why the Moon orbits the Earth. Bound systems are the universe's natural state at these scales. Departure is the exception, requiring specific conditions. Staying is just what happens when the energy accounting works out the way it works out. Which leaves the question the chapter opened with, what the universe cares about when it comes to the word leave, with something like an answer, though the answer is more of a reorientation than a resolution. The universe doesn't have a concept of departure. It has energy states and gravitational potentials and the mathematical conditions under which objects remain associated or drift apart. These conditions don't know about intentions, about inside and outside, about the felt experience of confinement or freedom. They are just conditions, physics operating in the way physics operates. Leave is a word built for a creature with a body, moving through spaces built for bodies, with edges scaled for bodies to feel and recognize. Applied to a galaxy, it works as a loose approximation, a way of asking whether escape velocity can be achieved, but it starts to shed its other connotations, the sense of departure, the sense of behind and ahead, the sense of a thing that persists after the leaving, waiting to be left. The Milky Way won't wait, it will merge, it will become something else. The solar system will remain gravitationally associated with the combined structure, while the container transforms completely around it. There's something almost restful about this, when it settles, and settles is the right word, because it doesn't arrive quickly. The impossibility of leaving isn't an imprisonment, because the thing that would do the imprisoning doesn't have walls. It's a gravitational situation, an energy accounting, a pattern of motion that the solar system is part of, and that is itself part of larger patterns, all the way up through the local group and the Virgo supercluster and the Laniakea supercluster, and the large-scale flows toward the great attractor. You're not inside a cage, you're inside a set of nested gravitational relationships, each one real, each one physical, each one a consequence of mass and motion and the geometry those things produce in space, time. The word leave doesn't quite fit, not because it's wrong exactly, but because it was built for a different kind of space. What you are inside is not a place that was built to contain you. It assembled itself from the same processes that assembled you, or rather, assembled the elements you're made of, which is the subject still waiting, patient and strange somewhere ahead. The matter in your body passed through processes distributed across this galaxy, and possibly others, across timescales that make the merger of Andromeda feel recent. That's not quite the next thing, but it's close. The origin of what you're made of is a different kind of inside story, not about where you are, but about where the pieces of you have been, and how far they travelled before arriving here. Iron. There's iron in your blood, not as a curiosity, not as a trace element, but as a functional necessity, the atom at the centre of each hemoglobin molecule that binds oxygen and carries it from the lungs to every cell that needs it. Without iron in the blood, the oxygen transport fails, the body fails. Iron is, in this very direct sense, load-bearing, and every atom of it was forged in a star. Not this star. Not the sun, which is too small and too cool to fuse elements heavier than helium in its core under normal conditions, and which will never in its lifetime produce iron through fusion. The iron in human blood was made in a sting, probably multiple stars across multiple stellar generations that lived and died before the solar system existed, before the cloud of gas and dust that would become the sun and its planets had begun to collapse. Before this region of the galaxy had the particular chemical composition it has now, the iron was here first, waiting dispersed through the interstellar medium when the solar system formed. How a star makes iron, or rather how the universe gets to iron through a sequence of stellar processes, is one of those stories where the steps are individually comprehensible, but the cumulative picture is strange enough that it takes a moment to accept as literal rather than metaphorical. Stars begin with hydrogen. The first stars, formed from the nearly pure hydrogen and helium left by Big Bang nucleosynthesis, had no heavier elements at all. They were pristine, chemically simple, massive enough in many cases to burn through their fuel quickly and die violently. When they died, they seeded the interstellar medium with the heavier elements their cores had produced: carbon, oxygen, neon, magnesium. The next generation of stars formed from this enriched gas, containing a slightly higher fraction of heavy elements, and when they died, they enriched the medium further. This cycle, stellar generations building chemical complexity through successive rounds of nuclear burning and violent dispersal, is why the universe today has the elemental composition it has, why a planet like Earth can exist, rocky and chemically varied, why biology is possible. Iron marks a specific point in this process. In the cores of massive stars, nuclear fusion proceeds up the periodic table: hydrogen to helium, helium to carbon, carbon to neon and oxygen, oxygen to silicon, silicon to iron. Each step releasing energy, each step possible because the products are more tightly bound than the reactants. But iron is the endpoint. Iron 56 is the most tightly bound nucleus in existence, the configuration of protons and neutrons that sits at the bottom of the nuclear binding energy curve. Fusing iron doesn't release energy, it requires it. When a massive star's core becomes iron, fusion stops. The energy source that had been holding the core up against gravity is gone. The core collapses in less than a second. The outer layers, still falling inward, bound off the suddenly rigid collapsed core in a shockwave that tears the star apart. A core collapse supernova, one of the most energetic events the universe produces. The iron that was in the core doesn't survive this, but the explosion produces conditions: extreme temperatures, extreme neutron fluxes, under which elements heavier than iron can be synthesized rapidly, and it scatters everything outward into space. The iron in blood almost certainly came from a supernova, possibly several supernovae, the contributions of multiple stellar deaths mixed together in the interstellar medium over millions of years before the solar system formed. There is no way to trace a specific iron atom to a specific star. The mixing is too thorough, the history too long, the interstellar medium too turbulent. But the origin class is clear: massive stars, core collapse, violent dispersal. The Sun is a third-generation star approximately, meaning the gas cloud from which it formed had already been enriched twice over, or some rough number of times, the generation framing is an approximation, by previous cycles of stellar birth and death. The heavy elements in the solar system, including every element in every human body, are the accumulated inheritance of stars that lived and died before the Sun existed. Some of those stars lived in what is now the Milky Way. Some may have formed in smaller galaxies that were later absorbed by the Milky Way, dwarf galaxies whose stellar populations were stripped and dispersed into the disk and halo over billions of years. The Milky Way has a history of mergers, written in the ages and chemical compositions and orbital properties of its stars, and the stars that enriched the gas cloud that became the solar system may have originated in structures that no longer exist as discrete galaxies. There's a specific element worth mentioning alongside iron, because its story is different enough to be illuminating: gold. Gold cannot be made in a supernova's core. The R process, the rapid neutron capture process by which elements heavier than iron are synthesized, can operate in supernovae under the right conditions, but the gold in the solar system is now thought to come primarily from a different event entirely: the merger of two neutron stars. Neutron stars are the collapsed remnants of massive stars after supernova, objects roughly 20 kilometers across but containing more mass than the Sun, or spinning rapidly, composed almost entirely of neutrons packed to nuclear densities. When two neutron stars spiral together, drawn inward over millions of years by the energy lost to gravitational wave emission, and finally collide, they produce a kilonova, a brief, intensely bright explosion that synthesizes and disperses enormous quantities of heavy R process elements: gold, platinum, uranium. In 2017, gravitational wave detectors and electromagnetic observatories together observed exactly this event. GW170817, a neutron star merger in the galaxy NGC 4993, approximately 130 million light-years away. The kilonova that followed produced, by estimates derived from the light curve, something on the order of several Earth masses of gold and comparable quantities of platinum and other heavy elements dispersed into the surrounding interstellar medium. The gold in a ring, or in the contacts of an electronic device, or wherever it happens to exist in your life right now, has the same origin. Neutron stars that collided somewhere in the Milky Way's history and scattered their contents into the gas that would eventually form the solar system. Where in the galaxy did these events happen? This is the question that makes the origin story stranger, because the answer is not here, necessarily. Not in this region of the disk, not at this galactic radius, not at this position in the spiral structure. The stellar processes that produced the elements now present in the solar system occurred distributed across the galaxy, and possibly in galaxies that were later absorbed into the Milky Way over a span of billions of years before the Sun formed. The interstellar medium, the gas and dust filling the space between stars, is not static. It circulates through the galaxy's disk on timescales of hundreds of millions of years, driven by turbulence, by supernovae shockwaves, by the density waves of spiral arms, by the gravitational perturbations of giant molecular clouds. Material dispersed by a supernova in one region of the disk doesn't stay in that region. It mixes, slowly but thoroughly, into the larger medium, which means the iron in blood might have originated in a star that lived at a different galactic radius, in a different arm, possibly on the other side of the disk. The gold might have come from a neutron star merger in a region of the galaxy that the Sun, in all its subsequent orbits, has passed through or near multiple times without any record of the event. The solar system formed from mixed-up material. The provenance of any given atom is, in general, unrecoverable. There's a specific thought that arrives here slowly that I want to try to articulate carefully rather than quickly. The usual version of this story, "we are made of stardust," a phrase so often repeated that it has acquired the texture of a platitude, points at something real but undersells one of its most interesting features. It isn't just that the atoms in a human body were once inside stars, it's that those atoms were inside stars in different places, at different times, in different parts of the galaxy, and that the mixing processes that brought them together to form the solar system erased most of the information about their individual origins. You are not made of one star's material. You're made of a sample of the Milky Way's cumulative chemical output, drawn from a large volume of space and a long span of time, mixed by the turbulent processes of the interstellar medium, concentrated by the gravitational collapse of a single cloud, and assembled into biology by the same physical and chemical processes that operated everywhere in the galaxy, where conditions allowed. You are, in this very specific sense, not from here. You are from a distribution of places and times that overlaps with here, but is not centered here, not bounded here, not belonging exclusively here. This has consequences for the never-leaving story that this chapter fits inside. The solar system cannot leave the Milky Way. That is, as established, a statement about energy and gravitational binding. The solar system doesn't have enough kinetic energy to escape the galaxy's gravitational potential well. It will remain associated with the galaxy through its remaining main sequence life, through the merger with Andromeda, through the long subsequent evolution of the combined structure, because the physics doesn't allow otherwise. But the matter the solar system is made of has already left multiple places. It has already travelled over billions of years and through multiple stellar life cycles, from wherever its parent stars were born to wherever they died, to the diffuse interstellar medium, and then to the collapsing cloud that became the solar system. The atoms now sitting still in a room have a travel history that spans galactic distances and deep time. The body is the destination of a long dispersal. The current stillness, the weight of it in a bed or a chair, is a temporary local concentration of material that was scattered across significant fractions of the galaxy before gravity pulled it here, into this configuration, into this form. The solar system has been at its current galactic radius, roughly 26,000 light-years from the centre, for its entire existence, moving around the centre rather than toward or away from it. But the material that makes it up doesn't share that address as a point of origin. The iron arrived from somewhere else. The gold arrived from somewhere else, from an event that may have occurred in a completely different region of the disk. The carbon, the oxygen, the nitrogen. Each element has a synthesis history that maps to different stellar populations in different parts of the galaxy, enriched over different timescales, dispersed by different mechanisms. You contain the galaxy's history in your chemical composition. Not metaphorically. The isotope ratios in your bones, if analysed with sufficient precision, carry traces of the nucleosynthetic history of the gas cloud that formed the solar system, which itself reflects the integrated stellar history of the region of the galaxy from which it drew its material. You are a local concentration of a distributed history. The galaxy folded some of itself into you. And now that fold, the specific configuration of atoms that constitutes a human body, is asking about the galaxy it came from, using the same atoms the galaxy provided for the purpose. There is something about this that resists being made neat. The temptation is to land on a symmetry. The galaxy made you, you contemplate the galaxy. Everything folds back into itself. And while that's not wrong exactly, it's too tidy for what's actually being described. The atoms in a body will outlast the body by an incomprehensible margin. The carbon will disperse back into the biosphere, then eventually the atmosphere, then eventually, over geological time, into the crust, and over stellar time back into the interstellar medium if the sun's evolution disperses the inner planets. The iron will follow its own path. The gold, wherever it is, will follow another. These atoms will not stay together. The configuration that makes them a person or a planet or a star is temporary in every case. The galaxy doesn't hold configurations, it holds matter. And matter circulates through configurations over time, which means the solar system's inability to leave the galaxy is, in a sense, an inability on the part of matter to escape a gravitational potential that it has been cycling through for billions of years in various forms. The current form, star, planet, ocean, body, is one configuration in a long sequence. The galaxy has had this material before in other forms. It will have it again. The question of where the pieces of you came from has a long answer and an incomplete one. The question of where they're going is similar. Both answers involve the same structure, this 100,000 light-year disk, this trillion solar masses of ordinary and dark matter, this gravitational well that defines the boundaries of everything discussed in this particular inquiry. What's left is to think about the Andromeda approach more carefully. Not the merger itself, but what the arrival means for the shape of the thing that holds all of this. And then, past that, the longest view available, the one that looks all the way to the end of stars. On a very dark night, away from cities in the right season, you can see Andromeda with the naked eye. Not the spiral, not the arms, not the bar or the bulge or the satellite galaxies attending its edges. Just a smear, a faint, soft elongation in the direction of the constellation Andromeda, slightly above and to one side of the Great Square of Pegasus, visible only if you look slightly to the side of where you think it is, using the rods at the periphery of the retina rather than the cones at the centre, the old sky observer's trick of averted vision that lets the more light-sensitive cells do the work. It looks like nothing much, a smudge, an imperfection in the sky, something you might dismiss as optical artifact or cloud if you didn't know what you were looking at. What you're looking at is a trillion stars. The light reaching your eye from that smudge left Andromeda approximately 2.537 million years ago. Not an approximation rounded for convenience, 2.537 million light years is the current best measurement, with an uncertainty of roughly 40,000 light years in either direction, which is itself a remarkable precision for a distance that size. The light left when Homo habilis was making stone tools in East Africa, when the genus that would eventually become human was just beginning the long cognitive elaboration that leads, among other things, to lying in the dark thinking about the source of a faint smudge in the sky. The galaxy you're looking at, in other words, is 2.537 million years old in the image it's presenting. The Andromeda visible tonight is a historical document, and it is closer than it was when that light left. Not by much, in absolute terms. The 110 kilometers per second at which Andromeda approaches the Milky Way means it has closed perhaps 350 billion kilometers during the 2.537 million years the light was travelling, which is a large number in everyday terms and a rounding error against 2.537 million light years. But the direction of motion is clear. The spectra of Andromeda's stars are blue-shifted towards shorter wavelengths by the Doppler effect of approach, and have been measured precisely enough that the radial velocity, the component of motion directly toward us, is well established. Andromeda is coming at 110 kilometers per second radially. There is also a transverse component, motion across the line of sight, measured by the Hubble Space Telescope and refined by Gaia, which found it to be relatively small. Small enough that the trajectory is nearly head-on. Not a grazing encounter, not a near miss, but a genuine interpenetration of the two galaxies' volumes in roughly 4.5 billion years. This number, 4.5 billion years, is worth holding without immediately reaching for context that scales it down or makes it manageable. The instinct to domesticate large timescales by comparison is understandable, but it costs something. 4.5 billion years is longer than the Earth has existed. It is longer than the Sun has been burning. It is nearly a third of the current age of the universe. And it is the time remaining before the two largest galaxies in the local group begin their first interpenetration. Not a collision in any sense the word normally carries. The average distance between stars in the Milky Way's disk is several light years. A light year is roughly 9.5 trillion kilometers. The stars themselves, even the largest, are measured in millions of kilometers across, which against light-year separations makes them effectively invisible to each other in terms of physical contact. Two interpenetrating disks of stars, each with these average separations, will pass through each other with a probability of direct stellar collision that is genuinely small. The stars will not hit each other, but the galaxies are not just stars. The interstellar medium, the gas and dust filling the space between stars, is spatially extended, and gas interacts with gas. When the two disks intersect, the interstellar media will collide and compress. This compression will trigger star formation at rates far exceeding what either galaxy produces in isolation. The merging system will briefly become a starburst galaxy, an object radiating enormous luminosity from the concentrated burst of new stars forming in the compressed gas. The gravitational dynamics of the merger are well studied through simulation. Two massive disk galaxies approaching on a nearly radial trajectory will not merge in a single pass. The first encounter will be violent in the sense of being gravitationally disruptive. The disk structures of both galaxies will be disturbed. Stars will be pulled into long tidal streams extending hundreds of thousands of light years. The overall morphology of both systems will change beyond recognition, but the two cores will not immediately coalesce. They will pass through each other and then, slowed by dynamical friction, loop back. A second pass, and eventually after several such oscillations over a span of perhaps 1 to 2 billion years following the first contact, the two galactic nuclei will merge into a single gravitational center. The supermassive black holes at the centers of both galaxies, Sagittarius, a star in the Milky Way at 4 million solar masses, and the black hole at Andromeda's center at somewhere between 100 million and 200 million solar masses, will eventually spiral together, losing energy to gravitational wave emission over an extended period, and merge into a single more massive black hole. That merger will produce a gravitational wave signal of extraordinary power, though there will be no human civilization present to detect it, and perhaps no civilization anywhere within range. Where will the Sun be during all of this? Probably, because the orbital mechanics of galaxy mergers are chaotic in the technical sense, sensitive to initial conditions in ways that make individual stellar trajectories unpredictable over these timescales, probably still orbiting somewhere in the combined structure. The Sun is not located near the galactic center, where tidal disruptions will be most severe during the merger. It sits in the outer disk, which will be disturbed but is less likely to be dramatically reorganized in the first pass. Simulations of Milky Way, Andromeda merger scenarios suggest a small but non-negligible probability, roughly 3% by some estimates, that the Sun could be gravitationally scattered into the outer halo of the combined structure during the merger, or even ejected into the local group as an unbound star. Small probability, but not zero. The chaos of the interaction makes certainty unavailable here. Most likely the Sun remains associated. Its orbit will be different, the ordered circular orbit of the current disk replaced by something more elongated, more inclined, shaped by the perturbations of the merger, but it will still be orbiting a gravitational center, still inside a gravitationally bound structure, still inside the thing that used to be two galaxies. The sky, during and after the merger, would be transformed in ways difficult to fully visualize. During the first passage, Andromeda's stars would populate the sky in a band or arc of extraordinary density, a second Milky Way in effect, visible from anywhere in either galaxy, the combined light of 1 trillion stars in the near sky. The tidal streams pulled from both galaxies would arc across the sky as luminous bands. The starburst regions, where compressed gas was forming new stars at high rates, would appear as brilliant knots of blue-white light, and over the billions of years of the merger's evolution, the sky would continue changing. The familiar disordered but stable stellar background of tonight, Orion, the Southern Cross, the stars of the Summer Triangle, all of them long since shifted from their current positions by proper motion but still present, would be replaced by configurations shaped by the combined stellar populations of the two former spirals, by the tidal debris of the merger, by the slowly settling orbital structure of the emerging elliptical galaxy. the word familiar stops applying. Everything visible from a surviving planetary surface will be unfamiliar, recognizably a night Sinbad sky, made of the same physics, the same hydrogen and helium and nuclear fire, but arranged into patterns that no map made today would match. And when the merger has realized, when the elliptical galaxy has reached dynamical equilibrium, which takes several billion years after the nuclear coalescence, what exists will be a single gravitationally bound structure containing the stars of both former galaxies, the combined dark matter halos of both, the remnants of the interstellar media of both, and orbiting near its outskirts probably, in some elongated path through the elliptical stellar population, the Sun, or its remnant. The Sun will have left the main sequence by then. It will have expanded through its red giant phase, probably engulfing Mercury and Venus and possibly the Earth, expelled its outer layers as a planetary nebula, and contracted to a white dwarf, a dense, slowly cooling ember of carbon and oxygen roughly the size of the Earth, but containing most of the original solar mass. The white dwarf will orbit Milky for a long time. White dwarfs cool slowly, radiating the thermal energy stored in their interiors over timescales of billions to trillions of years, dimming from white to yellow to orange to red to, eventually, a theoretical black dwarf, a cold, dark, inert remnant, though the universe is not yet old enough for any white dwarf to have cooled to this endpoint. They are all still warm, all still radiating. Here is where the metaphor finally arrives, and I want to be careful with it. The merger of Andromeda and the Milky Way is sometimes framed as a collision, sometimes as a transformation, sometimes as an ending. None of these quite captures the character of what's being described, which is less a dramatic event than an extended process, drawn out over billions of years, involving phases of disruption and phases of settling, producing a structure that contains the material of both galaxies without being either of them. It is closer in character to two rivers meeting, not crashing into each other. Rivers don't crash, they join, and the joining takes time and distance and produces a combined flow that carries water from both sources without the sources being separable in the result. The water doesn't know which river it came from. The combined river doesn't remember the confluence as a specific place. The stars of the Milky Way and the stars of Andromeda will orbit together inside Milky without any physical marking of which came from where. The mixing will not be complete. Stellar populations retain chemical and age signatures that allow astronomers to identify merger debris even billions of years after the fact. But in terms of dynamics, of orbital properties, of belonging to a structure, both populations will be equally inside the same thing. The fact that the merger is coming, that it is, in the language of orbital mechanics, already inevitable, already written into the current energy accounting of the local group, doesn't change anything about tonight. The 4.5 billion years between now and first contact is a number large enough that it makes no claim on the present. Andromeda is arriving. It has been arriving for as long as the Milky Way has existed. The approach has been continuous, slow, patient in the way that only gravity can be patient. Not waiting exactly, because waiting implies awareness, but persisting, which is what gravitational attraction does when given enough time and a negative total energy. The smudge in the sky, visible on dark nights with averted vision, is the approaching galaxy. 1 trillion stars, 2.537 million light-years away, closing at 110 kilometers per second. Nothing tonight requires you to do anything with this fact. It will still be true tomorrow. It will be true for 4.5 billion more years. The sky won't look different in the morning, and yet the merger frames something about the larger story of being inside the Milky Way, the story this whole inquiry has been following. The galaxy that cannot be left will not be left, but it will become something it currently isn't. The container transforms, the stars remain associated, the gravitational binding persists through the transformation, deeper than the structure it expresses itself through, more durable than the spiral pattern that gives the current Milky Way its shape. What holds things together is not the shape. The shape is a temporary expression of the underlying gravitational situation. The holding is more fundamental than the held form, which means the never leaving is not a property of the current spiral structure, not a feature of the disk or the arms or the bar. It's a property of the mass, the gravitational potential, the energy accounting, and those survive the merger. Inside Milkomeda, whatever orbits it stays inside Milkomeda, the name changes, the shape changes, the holding continues. There is more to the shape of this containment, more to what it means that the holding continues while the form changes. That thought moves toward what containment actually is, when the walls that seem to define it turn out to be optional. Begin with a body in a room, not abstractly. Specifically, the weight of it against whatever surface it's resting on, the particular pressure of a shoulder or a hip or the back of a skull against something solid. The faint warmth of the body's own heat reflecting back from the bedding or the cushion. The sound of breathing which mostly goes unnoticed because the auditory system learns to filter out sounds that repeat without variation. The room is dark or nearly dark. The window, if there is one, shows something. The orange residue of streetlight, the blue-grey of a cloudy night, or actual darkness and maybe stars. The body is inside the room. This seems like the simplest possible statement, and it is at one level. But inside is doing a lot of work in that sentence, and the work it's doing is different from the work inside does when applied to a galaxy. A room has walls. The walls are material boundaries, specific surfaces at specific locations made of specific stuff, occupying specific positions in space. The inside of the room is the volume enclosed by those surfaces, and the boundary between inside and outside is, within normal tolerances, precise. You can stand at the threshold of a doorway and be simultaneously almost inside and almost outside, but the ambiguity is spatial and small, a matter of centimeters, and it resolves definitively once you take another step in either direction. This is what containment usually means, a boundary that is locatable, material, and relatively sharp. The Milky Way has none of this. There is no surface, no wall, however thin, however permeable, however symbolic. The galaxy's boundary, and to whatever extent it can be located at all, which earlier chapters have explored at some length, is a statistical gradient, a region where density drops and the word inside loses confidence rather than snapping to an opposite. You could move outward from the sun's current position for 50,000 light years, watching the stellar density thin and the gas clouds become sparse and the gravitational influence of the galactic center attenuate, and at no point would you pass through a surface. There would be no moment of crossing, no threshold underfoot, no change in what you can hear or feel or smell, though all of these senses are irrelevant in interstellar space for reasons that have nothing to do with walls. So the room and the galaxy are not the same kind of container. This is obvious. What's less obvious is what kind of container the galaxy actually is, if not the wall and interior kind. The body is inside the room because the room was built around a volume of space and the body occupies that volume. The construction preceded the occupancy. The room didn't form from the body moved into a pre-existing enclosure. The solar system is inside the Milky Way because the solar system formed from material that was already part of the galaxy, already moving in galactic orbits, already chemically enriched by previous generations of galactic stars. already subject to the gravitational potential of the galactic mass distribution. The solar system didn't move into the galaxy, it condensed out of it. The galaxy was the medium, and the solar system is something that medium did in one small region over a particular span of time. This is the distinction that keeps pulling at the thought, the one that changes what containment means in this context. The room contains the body the way a vessel contains a liquid. The body is a discrete thing placed inside a pre-existing enclosure. The galaxy contains the solar system the way an ocean contains a wave. The wave is not a separate object placed inside the ocean, it is a pattern the ocean produced from itself, using its own material, following its own dynamics, and the wave's existence is not separable from the medium it arose in. The wave is inside the ocean, but it is also made of ocean. The ocean is not surrounding it from outside. This analogy softens at the edges, the way analogies do when pressed. A wave is a transient pattern. A solar system is a far more durable configuration that persists for billions of years and maintains distinct properties. An ocean wave carries no memory of its formation. The solar system carries the chemical signature of the specific cloud it formed from, the specific epoch of galactic enrichment that produced that cloud's composition, the specific angular momentum inherited from the cloud's turbulent rotation. The solar system is more individual than a wave, but the basic structure of the relationship, contained thing arising from containing medium, not placed inside it, holds. And this changes what it would mean to leave. A body leaving a room is a discrete object exiting an enclosure, returning to a space that is in some sense prior to and independent of the enclosure. The space out the room was there before the room was built. It will be there if the room is demolished. The body's existence doesn't depend on the room's existence doesn't depend on the body, and the leaving is a clean separation of two things that were always distinct. The solar system leaving the Milky Way, if it could, which it can't, but hypothetically, would be different in kind. The solar system would carry with it the chemical products of galactic stellar history, would carry the angular momentum imparted by galactic dynamics during its formation, would carry in every atom of every planet the record of nucleosynthetic processes distributed across the galaxy over billions of years. It would leave, in this hypothetical, as a piece of the galaxy that had separated from the rest, not as an independent object exiting a pre-existing enclosure, but as a fragment of a larger thing attempting to exist without the larger thing. The body can leave the room and remain fully itself. It's not clear the solar system could leave the galaxy and remain fully itself in any comparable sense. And this isn't about the impossibility of achieving escape velocity, which is a different, more concrete barrier. It's about the deeper entanglement of origin. And here is where this chapter's particular subject, what containment actually is, arrives at something that I find worth stating plainly, even at the risk of it sounding more definitive than I'm entirely confident it is. The galaxy is not containing the solar system the way a box contains its contents. The galaxy and the solar system are not two separate things in a container relationship. They are two scales of organization of the same material, the same gravitational dynamics, the same long physical history. The solar system is what some of the galaxy's matter is currently doing in one small region at this particular time. The galaxy is the larger process within which that smaller organization exists, and from which it is not, in any fundamental sense, separable. Containment, in the ordinary sense, the room and body sense, implies separability. It implies that the contained thing could in principle exist without the container, and that the container's boundaries are what currently prevent this. The galaxy's relationship with the solar system doesn't quite fit this. Not because the solar system couldn't theoretically have enough energy to escape the gravitational potential, That's a physical threshold question, not a question about the nature of the relationship. But because the solar system's material, chemical, and dynamical identity is a product of the galaxy, it supposedly can't leave. Step back further. The atoms in the body in the room, the iron in the blood, the carbon in the organic molecules, the calcium in the bones, the oxygen in the water making up the majority of cellular mass, are all products of galactic stellar processes. The body is made of elements that the Milky Way, through successive generations of stars, synthesized and dispersed into the interstellar medium. The body is, in a very literal sense, assembled from galactic output. The room, too, the materials of the walls, the floor, the ceilings, the silicon in the glass of the window, the iron in the steel of any structural members, the calcium in the concrete, if there is concrete, all of it traces back through the same chain. Geological processes, planetary formation, solar system condensation, interstellar medium enrichment, stellar nucleosynthesis. Everything in the room is made of the galaxy's material, so the body inside the room is not, in this deeper sense, a thing from outside the galaxy placed inside it. The body and the room and the building and the planet are all the galaxy's material, organized at different scales and in different configurations, doing different things. The room in this light is a tiny enclosed volume of the galaxy. The body inside it is also the galaxy. The containment happening at the room scale is, at the galactic scale, matter containing matter. The galaxy loosely arranged in one configuration, surrounding the galaxy tightly arranged in another configuration. This might sound like it's dissolving the distinctness of things, like it's arguing that because everything is made of the same underlying material, distinctions between things are illusory. That's not the argument. The body is real, the room is real, the solar system is real and distinct from other solar systems, and the Milky Way is real and distinct from other galaxies. The organizations matter, the patterns matter. The fact that a carbon atom in a bone was once in a star does not make the bone less real, or the person less themselves, or the room less genuinely a room. What it changes is the quality of the container relationship. The galaxy is not surrounding the solar system the way a jar surrounds air. It is the condition for the solar system's existence, the source of its material, the shaper of its dynamics, the gravitational structure within which it moves and from which it cannot fully separate, because separation would mean carrying the galaxy's products away from the galaxy, not escaping the galaxy from outside. You can't leave a process by carrying its products with you. The products and the process aren't separate enough for that. The body in the room shifts, small adjustments, a shoulder repositioned, a knee drawn slightly upward, the weight redistributing to find something more sustainable than whatever configuration preceded it. These are the small corrections of a body trying to rest. The tiny negotiations between the nervous system and the surface beneath it. The weight pressing down is gravity, the same principle, the same mathematics, the same curvature of space-time produced by mass, that holds the solar system in its orbit, that keeps the galaxy's disk from dispersing, that will eventually pull Andromeda through the Milky Way, that shaped the large-scale structure of the universe from the nearly smooth initial conditions of the early cosmos. The same thing at very different scales, the same relationship between mass and geometry, playing out from the scale of a resting body to the scale of galaxy clusters. And the body resting inside the galaxy is not, in the deepest sense, a separate thing inside a separate container. It is matter inside matter. The galaxy organized in this small region, in this temporary configuration, into forms that have weight and warmth and the specific pressure of a hip against a mattress. Forms that last decades rather than billions of years, forms that think and breathe and notice the dark, and then reorganize slowly and continuously into other configurations. Containment at galactic scales turns out to be something closer to membership than enclosure. Not a box with an inside and an outside, but a process with participants, and the participants are the process, and the process is what they're inside of. The inability to leave, the escape velocity, the gravitational binding, the energy accounting, is not a wall's rigidity, is the impossibility of separating a process from itself. You can try to carry a piece of it away from the whole, but the piece carries the whole's history in its atoms, its dynamics, its orbital properties. The leaving, even if it were physically possible, would not produce a clean departure. It would produce a fragment of the galaxy moving through space, taking the galaxy's record with it. The room contains the body the way rooms contain bodies, discreetly, temporarily, with walls that work. The galaxy contains the solar system the way it contains everything, not from outside, not by surrounding, but by being the medium from which it arose and within which its physical identity was made. That's a different kind of inside. And the pieces of that inside, the iron, the carbon, the calcium, the specific atoms now arranged into whatever is reading or listening to this, have been in many configurations before this one. They have been inside stars, inside supernova shockwaves, inside cold molecular clouds, inside the early solar system's turbulent disk of gas and dust, inside geological processes, inside biology. Each configuration was inside the galaxy. Each one was the galaxy's matter doing something for a while. This one is temporary too, which is not a sad observation, just an accurate one. The matter will remain associated with the galactic structure, or its successor, after Andromeda arrives, for longer than any human unit of time can honestly represent, inside, the whole time, in ways that the word inside only partially captures, but hasn't found a replacement for yet. The universe is currently in what cosmologists call the stelliferous era. Stellar, from stars. The era of stars. It began approximately 100 million years after the Big Bang, when the first stellar objects ignited, and it will end, by current estimates, somewhere around 100 trillion years from now, when the last star exhausts its fuel and goes dark. This is the era we're in, the one with light, the one with nuclear fire in the sky. 100 trillion years sounds final. It isn't the end of anything except stars. The universe has a timeline that extends far beyond the stelliferous era, into periods so remote and so dark that they have names: the degenerate era, the black hole era, the dark era, but no light, no chemistry of the kind that produces planets or biology or anything recognizable as physical complexity in the sense the word usually implies. These later eras are the domain of theoretical physics rather than astronomy, populated by cooling white dwarfs and ancient neutron stars and the slow decay of protons, if protons decay, which remains unconfirmed, and black holes evaporating over timescales that make 100 trillion years seem immediate. The stelliferous era is, against that backdrop, a brief, bright interval. We are inside it. We are near its beginning, actually. 13.8 billion years into a 100 trillion year era is roughly the equivalent of being 13 minutes into a 24-hour period. The stars have barely started, but they will end. The end of the stelliferous era won't arrive as a single event. It will be a slow process of attrition, the gradual exhaustion of the interstellar gas and dust from which new stars form. As existing generations of stars lock up more and more of the available matter in long-lived remnants, and as the rate of a new star formation falls over billions and then trillions of years towards zero. The last stars won't be like the Sun. They'll be red dwarfs. The small, cool, dim, and extraordinarily long-lived stars that constitute the majority of the Milky Way's stellar population today. Red dwarfs burn hydrogen so slowly, at temperatures so much lower than larger stars, that their main sequence lifetimes extend to trillions of years. The smallest red dwarfs, objects just barely massive enough to sustain hydrogen fusion, will burn for 10 to 14 trillion years before exhausting their fuel. The Sun will have been a white dwarf, slowly cooling in the dark for nearly 10 trillion years before the last red dwarfs go out. What will the galaxy look like then? The galaxy that is now the Milky Way, or rather the merged Milkomda that the Milky Way will have become long before the last stars die. The merger with Andromeda will be ancient history by the time the last red dwarfs approach their end. The dynamical settling of the merger, which takes a few billion years, will have completed perhaps 90 trillion years before the final stars exhaust themselves. Milkomeda will have reached something like dynamical equilibrium, an elliptical galaxy, stars orbiting in a roughly spheroidal distribution, the ordered rotation of both original disks replaced by the randomized orbital motions that characterize elliptical galaxies. Most of the stars in this future galaxy will already be dark or dimming. The large, bright, fast-burning stars that dominate the light output of galaxies today will have been gone for tens of trillions of years. The medium-mass stars, sun-like and somewhat smaller, will have exhausted themselves and left behind white dwarfs scattered through the galactic volume, cooling over the eons from white to yellow to orange to red, fading. The galaxy's light output will have been declining for a very long time by the point the last red dwarfs are burning. What remains lit by the time of the last stars will be scattered and dim, widely separated points of deep red light, each one a small cool star burning its hydrogen slowly to the end, separated by distances so large that any remaining planetary system would see the others as barely distinguishable from the background of very faint and very cold light. There's a specific red dwarf worth noting here, not because it will be the last star, that's unknowable with any precision, but because it illustrates what the last stars are like. Proxima Centauri, the nearest star to the Sun at 4.24 light-years, is a red dwarf with a mass of about 12% of the Sun's. It is the kind of star that, if it burns slowly enough, might still be fusing hydrogen roughly 4 trillion years from now, long after the Sun has completed its entire life cycle and left behind a white dwarf cooling toward invisibility. Proxima Centauri will outlive the Sun by a factor of several hundred, and by the standards of red dwarfs, Proxima Centauri is not even especially small. The smallest red dwarfs, objects orbiting in the galaxy today, burning so slowly their light is barely detectable, will last longer still. The last star will be one of these, a small, cool, dim object fusing hydrogen at a pace so unhurried that the process will have taken trillions of years, surrounded by a galaxy that is mostly dark, mostly cold, filled with the white dwarf remnants of everything that burned before it. And then it too will exhaust its fuel. What happens when a red dwarf exhausts its hydrogen is different from what happens to larger stars. There is no red giant phase. Red dwarfs are fully convective, meaning their entire mass circulates through the fusion zone rather than developing a layered structure that leads to shell burning and expansion. When the hydrogen runs out, the star simply contracts and cools, fading through a brief period as a blue dwarf, a theoretical phase, not yet observed because no red dwarf in the current universe is old enough to have reached it, and then becoming a white dwarf, a slowly cooling remnant. No explosion, no planetary nebula, no dramatic dispersal of material back into an interstellar medium that no longer has the density or temperature to form new stars anyway. Just a contraction, a fading, a transition from dimmer massive star to dimmer passive remnant. The last star in what was once the Milky Way will end quietly. The white dwarfs will persist. This is worth noting, because the end of stars is not the end of matter, and the matter still has a long story ahead of it. White dwarfs are a stole against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that doesn't depend on temperature and doesn't diminish as the white dwarf cools. A white dwarf at absolute zero would still be supported against collapse by electron degeneracy pressure, assuming it's below the Chandrasekhar mass limit of about 1.4 solar masses. Below that limit, white dwarfs are effectively permanent on timescales the universe has yet to approach. So the galaxy, the Milky elliptical, or whatever it has become by then through further interactions with other local group members, will enter the degenerate era not as an empty volume, but as a vast collection of dark remnants, white dwarfs, neutron stars, black holes. The matter is still there, the stars are gone. The degenerate era extends from roughly 100 trillion years to somewhere around 10 to the power of 40 years, a number so large that scientific notation is the only honest way to write it, and even in scientific notation it resists intuition. During this era, white dwarfs continue to cool eventually, in principle over timescales longer than the degenerate era itself for the coolest and most recently formed, fading toward the theoretical black dwarf state, an inert, cold, dark object made of carbon and oxygen crystallized into a structure denser than any normal matter, emitting essentially no radiation at a temperature indistinguishable from the cosmic background. No black dwarf is believed to exist yet. The universe isn't old enough. The cooling time for a white dwarf to reach black dwarf temperatures, genuinely cold, genuinely dark, is estimated to exceed the current age of the universe by many orders of magnitude. The oldest white dwarfs in the Milky Way today are still warm enough to be detected, but they are cooling, all of them. The direction of travel is toward cold and dark, and nothing in the physics of degenerate matter reverses it. What will the galaxy, the gravitationally bound collection of dark remnants that was once the Milky Way, be doing during all of this? Orbiting mostly. The dark remnants will continue following their orbital paths through the galactic gravitational potential, which persists even as the visible stars go out, because the dark matter halo, the vast invisible structure responsible for the majority of the galaxy's mass, is not made of stars and does not go through stellar death. The dark matter halo simply continues, unchanged in its gravitational contribution, holding the collection of dark remnants together through the degenerate era and beyond. Gravitational interactions between orbiting objects will occasionally scatter some dark remnants to higher orbits, and some to lower ones, with those falling inward eventually accreting onto the central black hole, the merged supermassive black hole that formed during the Andromeda merger, grown larger over the eons by accreting matter, now sitting at the centre of a dark galaxy and still pulling in whatever passes close enough. This scattering process, operating over timescales of 10 to the power of 19 to 10 to the power of 20 years, will gradually deplete the galaxy's stellar remnant population, not by destroying them but by ejecting them into the intergalactic void. One by one, dark remnants will be flung out of the galaxy on hyperbolic orbits, carrying with them the kinetic energy gained from the gravitational interaction, leaving the remaining galaxy slightly more tightly bound with each ejection. There's a question that this chapter keeps circling without quite landing on, and it's the question of what the word galaxy means after the stars are gone. The dark matter halo will remain. It doesn't decay on any timescale that current physics describes. Dark matter, whatever it is, doesn't participate in the processes that lead to stellar death or white dwarf cooling or black hole evaporation. The gravitational potential produced by the dark matter halo will persist essentially unchanged through the stelliferous era, through the degenerate era, through the black hole era. So there will be a gravitational structure. There will be a region of space with higher mass density than the surrounding universe, producing a potential well, holding whatever matter remains associated with it. By that standard, gravitational coherence, the galaxy persists long after the last star, but galaxy is a word built for stellar systems, for structures whose defining characteristic is light, the light of stars, the light of gas clouds ionized by stars, the light scattered by dust illuminated by stars. A gravitationally coherent structure containing only dark remnants and dark matter isn't a galaxy in the sense the word was made for. It's something else. Something without a good name yet, because nothing like it exists yet, because the universe hasn't reached that state, because the stelliferous era still has roughly 99.986% of its duration remaining. The last star. It will be somewhere in this structure, or in its intergalactic exile if it has been scattered out, though the probability favours it remaining associated galactic remnant through most of its life. It will be small, very dim, burning at a temperature cool enough that its light peaks in the infrared rather than the visible spectrum. Red enough that human eyes, if they existed, would see it only as a faint ember in an otherwise dark sky. It will have planets, possibly. Red dwarfs frequently host planetary systems, and the planets of the last star will have been orbiting it for trillions of years, through the entire death of all the other stars, through geological timescales that make Earth's 4.5 billion year history look like a prologue. Whether anything lives on those planets is a question physics cannot answer. Life's requirements are not fully understood even for the one case we have evidence of, and whether the slow, dim, infrared light of a late-phase red dwarf is sufficient to drive the chemistry that produced biology here, whether the extreme age of the system produces or prevents the conditions life requires, is genuinely open. Probably not. Probably the last star's planets are dead or never lived. But the uncertainty is honest rather than pessimistic. And then the fuel runs out, the convection stops, the core cools, the star contracts, the last light in what was the Milky Way, the light produced by nuclear fusion, the light that has been the defining feature of the galaxy since its first stars formed roughly 13 billion years ago, goes out. What remains is the dark matter halo, the central black hole, the scattered remnants of white dwarfs cooling toward absolute zero, and the gravitational memory of everything that burned here. The night is quiet enough that the small sounds of the house become audible. The refrigerator's compressor, the settling of the structure, whatever animals are outside doing their nocturnal work. These sounds are the present, and the present is a specific moment inside the stelliferous era, near its beginning, when the galaxy still has light in it, and the night sky still has stars in it, and the atoms of a human body are still in the configuration that makes them capable of thinking about what comes next. The last star isn't a cause for anything tonight. Not grief, not urgency, not the particular vertigo that comes from trying to hold very large numbers of years in a mind built for decades. It's just the far end of a period that started long before the solar system formed and will continue long after it ends. We are inside the lit part of this, the brief era when galaxies make stars and stars make light and light makes things like seeing and growing and knowing possible. The lit part won't last forever. It is, by any honest accounting, lasting right now. Begin where this started. A room, a body in it, the ordinary weight of things pressing down in the ordinary way, the specific heaviness of late night, the kind that collects in the eyelids and in the shoulders, and in the particular quality of attention that stops reaching forward and starts simply resting where it is. That's where this whole inquiry began. Not with the galaxy, technically, with the felt texture of being somewhere, of having a location, of the location having edges, of edges implying the possibility of crossing them. And 12 chapters later, the room is still here. The body is still in it. The galaxy is still outside, or rather, the galaxy is still everywhere, including inside the room, including inside the body, including in the atoms of the walls that seem to separate inside from outside, but are, themselves, made of the same galactic material as everything else. Nothing has changed, and the understanding of nothing has changed considerably. This chapter doesn't close the inquiry. That's worth saying plainly before the shape of a final chapter creates expectations that the subject doesn't support. There is no conclusion available for the idea that you cannot leave the Milky Way, not because the idea is unresolved, but because it doesn't have the kind of ending that conclusions require. It's not a problem, it's a condition. And conditions don't conclude, they persist, and you either become more familiar with them or you don't. What has accumulated over the preceding chapters is something like a portrait of being inside. Not the inside of a box, not the inside of a system with clean boundaries, but the inside of a process. A vast, ancient, still-running process that began with the gravitational collapse of gas clouds in the early universe, and that has been producing and destroying and reorganizing matter ever since, including the matter that is currently arranged into a person reading or listening to this in a dark room somewhere on the surface of one of its smaller products. The solar system cannot leave the Milky Way. This is, at its core, a statement about energy. The solar system's total mechanical energy relative to the galaxy's gravitational potential is negative. It doesn't have enough kinetic energy to climb out of the gravitational well it sits in. To leave, it would need an additional input of kinetic energy that nothing in the solar system's natural dynamics provides. The escape velocity is approximately 550 kilometers per second. The solar system is not moving at 550 kilometers per second relative to the galactic center. It is, and will remain, gravitationally bound. That's the physics of it. Clean, unambiguous, settled. But the physics doesn't fully describe what it means to be inside, and the preceding chapters have been accumulating a different kind of portrait alongside the physical one. The solar system didn't arrive in the Milky Way. It formed from it, condensed out of the galaxy's interstellar medium, inheriting the galaxy's chemical history in its elemental composition, inheriting the galaxy's dynamics in its orbital properties, carrying in every atom of every planet the record of nucleosynthetic processes distributed across galactic space and deep time. The insideness isn't a property that was imposed when the solar system entered some bounded region. It's a property that has been present since the solar system's first moment of existence because the solar system is a piece of the galaxy organized at a smaller scale. You don't leave the thing you arose from by moving through the thing you arose from. The logic of departure requires a separateness that isn't quite there. And the container itself, the Milky Way, the galaxy, the 100,000 light-year disk of stars and gas and the invisible dark matter halo surrounding and outmassing all of it, is not permanent. It will merge with Andromeda in roughly 4.5 billion years, becoming something structurally unrecognizable as either of its component galaxies. The spiral arms will be gone, the disk will be gone, the ordered rotation that currently defines the galaxy's dynamics will be replaced by the randomized orbital motions of an elliptical galaxy containing the stars of two former spirals. The Milky Way, as a recognizable structure, will end, and the solar system or its remnants, the Sun having completed its main sequence life and contracted to a white dwarf long before the last red dwarfs go out, will remain gravitationally associated with the combined structure. Still inside, still bound. The container changed beyond recognition, the binding unchanged. What this suggests, and what has been building across the whole of this inquiry, is that the never leaving isn't really about the Milky Way specifically. It's about gravitational binding, about what it means to be a piece of a larger gravitational structure, to have formed from it, to orbit within it, to carry its chemical record in every atom. The Milky Way is the current name for the gravitational situation the solar system is inside. When the name changes, when the structure transforms through merger and becomes Milkomeda, and then whatever Milkomeda becomes after further interactions over trillions of years, the binding continues under a different name in a different shape. The departure that can't happen isn't a departure from the Milky Way specifically. It's a departure from gravity, from the accumulated mass that produces the potential well, from the condition of being gravitationally associated with a structure large enough to hold things together against the general expansion of the universe. That departure isn't available. Not at any speed the solar system can reach or will ever reach through natural dynamics. There's a specific quality to this kind of impossibility that distinguishes it from other kinds, and I've been trying to find the right way to describe it throughout this chapter, but without quite landing. It's not imprisonment. Imprisonment implies a bounded space with exits that are locked, and an interior distinct from an exterior, and an agent maintaining the boundary. The galaxy has none of these, no locks, no guard, no wall distinguishing inside from outside in any sharp sense. It's not limitation in the ordinary sense, the kind of limitation that comes from insufficient technology, from resources not yet available, from problems not yet solved. The escape velocity barrier isn't a technology problem. Even with arbitrarily advanced propulsion, the energy required to achieve 550 kilometers per second of sustained velocity is simply the energy the galaxy's mass demands. Better engineering doesn't change the gravitational potential, it's closer to. And here the language starts to drift, so I'll try to stay close to the literal. It's closer to being a part of something than being inside something. Parts don't leave holes. They can be separated from holes, but the separation doesn't produce a part that is now outside the hole. It produces a fragment carrying the hole's properties, moving through a space that the hole's gravity still reaches into, still decelerating the fragment, still maintaining a gravitational relationship across whatever distance the fragment achieves. Even a solar system moving at escape velocity, which this one isn't, would remain in a gravitational relationship with the galaxy. The relationship would thin and weaken over distance, never reach zero, never fully release. There's no outside where the outside is truly free of inside. The dark matter halo extends hundreds of thousands of light years. Beyond it, the local group's combined gravity reaches further still. Beyond that, the streaming motion toward the great attractor continues, nested inside the large-scale structure of the universe, the filaments and voids, the patterns of matter distribution that trace back to the density fluctuations of the early universe. There is no location in the observable universe that is free of gravitational influence from something. The inverse square law ensures that gravitational force falls off with distance, but it doesn't reach zero. Every piece of matter in the universe is gravitationally coupled, however weakly, to every other piece of matter in the universe. This means the never leaving is, at its deepest, a statement about the universe's structure rather than the galaxy's specifically. Leaving the Milky Way would mean entering the local group's broader potential. Leaving the local group would mean entering the Virgo supercluster's influence. Leaving the Virgo supercluster would mean moving through the large-scale flows toward the great attractor. And so on, not infinitely, because the universe's accelerating expansion means that sufficiently distant regions are causally disconnected, carried beyond the event horizon by the expansion of space itself. But the nested gravitational relationships extend very far. The solar system is bound to the Milky Way specifically. Beyond the Milky Way, it would be bound to the local group. Beyond that, other structures. The hierarchy doesn't provide an outside in any clean sense, just progressively weaker gravitational associations with progressively larger structures. What the body knows of all this tonight is nothing. Not in a failure of perception sense. In the most literal sense. The vestibular system reports no motion. The skin reports no pressure from the velocity. The inner ear reports no acceleration from the orbital dynamics. The body is at rest, or near enough to rest that the word applies, and the galaxy's hold on it is indistinguishable from the absence of a hold. This is the condition, the normal condition. The condition that has been the normal condition for every human that has ever existed, and for every living thing before humans, and for every non-living thing before life. The solar system has been inside this gravitational situation for 4.6 billion years, and for the overwhelming majority of that time, nothing in the system had any awareness of it. The awareness is recent. The condition is ancient. The room will still be here tomorrow. So will the galaxy, so will the gravitational binding, the dark matter halo, the slow orbital mechanics of the sun around the galactic center. The approach of Andromeda still 4.5 billion years away. The last red dwarfs still trillions of years from their ends. All of it persisting without urgency, without drama, in the way that the largest and most durable features of physical reality persist, not by trying, not by maintaining themselves against some force of dissolution, but simply by being what they are in the conditions that produce them. The galaxy holds the solar system, the way the solar system holds the planets and the planets hold their moons, not by choice, not by effort, but by the simple geometry of mass and motion, by the curvature of space-time that mass produces and that objects moving through space-time follow. The body in the room is part of this, not metaphorically. The atoms of it, the mass of it, the gravitational presence of it, however negligible against galactic scales, are part of the same accounting. They curve space-time too, by an amount so small it would never appear in any measurement relevant to galactic dynamics, but by the same principle. What does it feel like to be inside something you can't leave and can't fully see, and didn't choose and arose from and carry with you in every atom? It feels like this, like a room at night, and a body in it, and thoughts that arrived without being summoned, and the specific weight of late-night attention that has gone somewhere it doesn't usually go and is now finding its way back toward rest. It feels like the ordinary texture of being somewhere, which is... I keep returning to this, and I'm not sure if that's because it's true or because it's the easiest place to land, which is maybe the right answer. Not a comforting answer, not a dramatic one, just the accurate one. Being inside the Milky Way feels like being alive in a place, because that's what it is. The atoms in this body have been inside this galaxy for longer than the solar system has existed, inside previous stars, inside the interstellar medium, inside the molecular cloud that collapsed to form the sun and its planets. They will be inside this galaxy, or its successor after Andromeda arrives, after Milky settles into its elliptical form, for longer than the sun has left to burn. The current configuration, the particular arrangement of atoms that constitutes a person in a room at night, is temporary. Very temporary against the timescales this inquiry has been moving through. A few decades of biological existence against trillions of years of galactic lifetime. But temporary doesn't mean less real. The wave is real while it's a wave. The configuration is real while it's configured. The person is real while the atoms hold the form. And the galaxy will hold the atoms long after the form has dissolved and the atoms have redistributed into other configurations, other forms, other temporary arrangements of the same matter inside the same gravitational structure. There's no departure, not because the exits are locked, because the relationship between the solar system and the galaxy is not the relationship between a tenant and a building, a discrete thing inside a pre-existing enclosure, able in principle to pack and leave and find another building. It's the relationship between a piece of something and the something it's a piece of, and pieces don't leave holes. They can be separated, they can move, they can become part of other configurations, but they carry the whole's properties with them, and the whole's gravity follows them, and the following never reaches zero. The Milky Way doesn't need walls, the geometry does the work. And if you've been here for all of this, for the edges that wouldn't sharpen, for the dark matter that couldn't be seen, for the escape velocity that named its own impossibility, for the stars you're made from that didn't start here, for the Andromeda that's arriving, for the last star that will burn quietly and go out, then something in this inquiry has been in the room with you for a while. That's enough. That's what this kind of thinking is for, not to solve, not to conclude, but to sit with, for however long the night allows, and then to set down gently and let rest. The galaxy will still be there in the morning. It will be there for a long time. You don't have to do anything with that. You don't have to hold it or remember it or carry it anywhere. It's already holding you. If this found you somewhere quiet, and something in it settled, a subscribe helps more people find their way here. And if you know someone who thinks best in the dark, send this their way. That's how this kind of work travels.